I hope now when I am changing the slide, it is visible.
Yes, sir.
Okay.
Yes, sir.
So this particular map, the solar PV potential of India, so this has been prepared by National Institute of Solar Energy in 2015. And we observe that this 748 gigawatt peak. So this is a very huge value. So there is some fine print which is written here and it is not clear. So let me just uh, enlarge it. Okay. So how this particular value has been arrived at? So first of all, we know that for solar photovoltaic installations, you cannot actually cover the agricultural land, because then it will stop the sunlight falling on plants and their growth will be hindered. So in this calculation, only wasteland in every state has been considered. So that wasteland is not used for any other human use. So it can be the photovoltaic panels or plants can be installed on that wasteland. And also it has been assumed that in about 1 square kilometer, 50 megawatt peak of SPV plants can be installed. And also the rooftop component has not been excluded. Rather, some like it is mentioned here, on factories and workshops which have very big roof areas, or if we consider that 20% of such installations can have more than 50 kilowatt peak installation, and likewise for hospitals, hotels, some temples and mosques, likewise schools and colleges. So all the possible buildings are considered for rooftop calculation also. Okay, including the residential buildings. So it turns out the total installed capacity, the total capacity that we can install using this particular calculation is about 748 gigawatt peak. And remember, this calculation was done way back in 2015, and the average module efficiency was taken as 15%. But nowadays, modules with efficiencies 18% and higher are already available in the market. And in the near future, in the next 4 to 5 years, we can expect modules with more than 20% efficiency. So in fact, this solar potential, which was earlier estimated to be 748 gigawatt peak, this may be even higher, because technologically we are going for more and more efficient modules. But this is just to give us an indication. Yes, solar PV itself, so we are not considering right now solar thermal. So solar PV itself has a huge potential. And as expected, Rajasthan, because the wasteland area in Rajasthan is much higher compared to other states, and it is also area-wise, it is the largest state in India. So its solar potential is the highest, 142 gigawatt peak. Chhattisgarh, although Chhattisgarh is not a small state, it is a big state comparing states like Himachal, Haryana, Punjab, and northeastern states. But the solar potential here is slightly less compared to other states because we know the reason. More than 35% area is forest area, and there are many protected or reserved forests also. So we cannot have huge installations in forest zones due to environmental reasons. Okay, so this particular value is limited. But anyhow, 18 gigawatt peak is also not a small value. And in fact, as of 31st March, Chhattisgarh has not even installed 1 gigawatt peak of solar photovoltaics. So in Chhattisgarh, there is a huge scope of installation as well as photovoltaics research. Okay, let us move forward. Please let me know in case the slides are not visible. Okay, talking about the Indian power sector, so this data is updated up to 31st March 2021. So the total installed capacity in India is 383 gigawatts. And out of it, almost 1/4, 25% is renewable energy. So in this regard, India is doing very well. That in the past 10 years, due to this Jawaharlal Nehru Solar Mission and the setting up of various agencies for promotion of solar energy and other renewable energy sources, we have achieved a good mix of renewable energy in our electricity sector. But still, as we can see, the dominance of thermal power is still there. But in our lifetime itself, we'll see that this majority of the power will be coming from renewables. All the government policies are favoring the growth of renewables, not only solar, but other technologies like wind, biomass, and small hydro. So one point I would like to highlight here is this hydro power plants that we are seeing. These are very large hydropower plants. Okay, so these large hydropower plants, they submerge large parts of land underwater, so they are not considered as renewable energy sources. Only small hydropower plants. So typically, a few 100 kilowatts or less than say 5 megawatt, only they are considered as renewable energy sources. Otherwise, big hydropower plants are always categorized as conventional sources only. Okay. And this is the status of renewables. So the total installed renewable capacity is about 95 gigawatt, and wind and solar both are almost on equal footing. So ground mounted solar and solar rooftop combinedly, they are about 42%, and roughly 42% is the contribution of wind. But the Jawaharlal Nehru Solar Mission, National Solar Mission, so it was actually updated some years back. So the target is now to achieve 175 gigawatt of renewable capacity. And out of this, 100 gigawatt is to come only from solar photovoltaics. So government is pushing up actually the solar PV installations. And as of now, as of 31st March 21, you can observe that the total installed capacity of solar is about 40 gigawatt peak. Okay, 40 gigawatt peak. So still we have to actually install about 60 gigawatt peak more in the next year or so. So as of now, it appears difficult to achieve this capacity by December 22 because of the prevailing pandemic situation and all. But yes, in very near future, in just 1 or 2 years, 2-3 years, we may be able to achieve this 100 gigawatt capacity. And we'll just see how we can actually, how we ourselves as individuals can contribute to this particular target. Okay, now let us talk about solar radiation. So the sun god is the ultimate source of energy. So barring say nuclear energy, almost all forms of energy are directly or indirectly derived from sun. So I would request you to note down this particular parameter here. This is the radius of sun. So this will be useful in some calculation that we are doing. If it is not visible, let me just read it out to you. The mean radius in kilometers of sun is 695,700. 6,95,700 kilometers. So this is the mean radius of our sun. Okay, so this will be useful for some calculations that we'll be doing shortly. Okay, let us proceed. These are some other observational parameters that we have. Okay, so the mean distance between Earth and suns in million kilometers, it is 149.6. Okay, so I request all of you to please note down this value also. So first is the radius of the sun. Second is the mean distance between Earth and sun. So 149.6 million kilometers, and the other was 6,95,700 kilometers. So this is the Earth sun distance, and that was the sun radius, solar radius. Okay. Now we have this term irradiance. The other common terms that you find in literature are radiation or irradiation. So whenever we are basically talking about irradiance, so the units are in watts per meter square, power received per unit area. And in this particular y-axis, you will see we are showing the spectral dependence. So by spectral dependence, we mean how much energy at each wavelength is being received. So this is the visible region between 400 to 700 nanometer, and we observe that the solar radiation or irradiance has a peak around the yellow region. So that is why we call our sun as a yellow star, because its spectral maxima is in the yellow green region. Okay. Now, a huge amount of energy, right from very high energy ultraviolet rays to very low energy radio waves, is emitted by the sun. Okay, but more than 99% of the energy is received in this from UV to far infrared or near infrared region. Okay, so this ultraviolet, visible, and the near infrared region up to 4 micron, they constitute the bulk of the energy received from the sun. Since maximum energy is received in the visible area, so maximum research focus till now has been on the development of cells or devices which utilize the visible or the near infrared spectrum of our sun. Okay, so ultraviolet, we know it is blocked by the ozone layer and it is dangerous to life. So ultraviolet is not very useful per se for use in photovoltaics or other devices. Okay, so this is the radiation part, and this particular radiation corresponds to a black body whose temperature is 5778 Kelvin. So please note down this particular temperature value also, 5778 Kelvin. Now there are two types of curves shown here. One is in yellow and the other is in red. So yellow spectrum is the spectrum that we receive outside our atmosphere. There is no absorption because of atmospheric gases. And this red colored spectrum that you observe, so it is what we get here on the Earth's surface. So you can observe that there are various valleys here. So there are various gases, like for example, bulk of this energy is absorbed because of water vapors. So water vapors, H2O molecules, they absorb at various wavelengths. So you can observe that this peak is somewhere around 900 nanometer, and then again around 1300 nanometer you see huge absorption by the water vapors. So all these things have to be considered while we are designing our solar cells, or when we are and since the distribution of water molecules also varies on Earth, so how much power you can generate in Rajasthan and how much power you can generate in say Lakshadweep or Andaman and Nicobar Islands, that will vary. Okay, so because of these atmospheric effects, we need to know about the solar spectrum. Okay, so let us move forward. Okay, so I hope the slide is visible. So what we are required to do is, our first problem here is to find out the solar constant. So what is solar constant? So solar constant is typically represented by the symbol G, and in a subscript you have S, or sometimes SC is also written. So basically this is a flux density. Flux of what? The solar radiation. So how much solar radiation per unit area is received on Earth. So how do you measure it? So normally it is measured using satellites. So we have satellites, even sun observational satellites, which are orbiting Earth. So they can measure this radiation. But right now, we'll try to calculate the solar constant from our basic knowledge of physics that we have studied in our UG undergraduate courses. How we can calculate the solar constant, that is how many watts per meter square are incident on Earth. So we know the famous Stefan Boltzmann law. Okay, what does it state? That the amount of energy or amount of irradiance emitted by a black body, that is I, so it is related to fourth power of its temperature. So the value of T, we already know, 5778 Kelvin, and this Stefan Boltzmann constant sigma, its value is written here. So it is 5.6703 into 10 to the power minus 8 watts per meter square per fourth power of Kelvin, that is temperature. Now I request you to just find out the value of I, and if some of you have any idea, you can just share in the chat box how we can basically calculate the solar constant. The problem here is simple. We want to calculate how many watt per meter square do we get on Earth's surface. I hope the problem is clear to all of us. So I had told you to note down the small r and capital R value, that is the radius of sun and the Earth sun mean distance. Maybe just think over it for a few seconds. Anyone has any idea how we can go about solving this question? You can type in chat box if you want to say anything. Okay, so till now I have not got any response. Anyways, let us see how we can solve this type of problem. So first of all, let us calculate this value of I. I is equal to sigma T to the power 4. So since T is of the order of 10 to the power 3, that is we are talking about thousands, so you will get a very huge value of I. Or in other words, a huge value of radiation is being emitted by the sun. So this is the relation that we can use. So if to find out the solar constant S or G, sigma T to the power 4, and this has to be multiplied by 4 pi r square divided by 4 pi capital R square, where small r is the radius of the sun and capital R is the Earth sun distance. Now can you tell me why we have used this factor? Anyone would like to share their opinion? So this is how we are basically calculating solar constant without doing any measurements. Just from our basic knowledge of thermodynamics, we are calculating this. So the idea is, you have the sun here. It is radiating. It is a sphere radiating in all directions. Okay, so we are taking the surface area of this sphere as 4 pi r square. So this is the basic knowledge that we all have. So this huge amount of energy, sigma T to the power 4, is being radiated by a surface whose surface area is 4 pi small r square. Okay, so it is radiating in all directions. But now talking about the Earth, so it is orbiting the sun at a great distance of 150 million kilometers. Okay, so assuming that there is no energy loss, So the energy radiated by this small sphere is now available at this big sphere, whose radius is equal to the Earth-Sun distance. All right. So what happens? Basically, the same energy is now distributed over a very large surface area. Because Earth is very tiny compared to the Sun, so the amount of energy that it is receiving here is very less compared to what is actually being emitted by the Sun here. Okay, so if we perform these calculations, so you can perform these calculations later on using your calculators. So the value that you get, so this is the inverse square law that actually we were talking about. So since the R square dependence is there, so as you are basically if you are at point A and if you are at point B, and the distance, if this is R and this total is 2R, then basically the irradiance at point B will be 1/4 of the irradiance at point A. So this is a simple inverse square law that we are talking about. So this is the value that you will get. 1367 watt per meter square. Okay. Now, NASA, ISRO, all of the space agencies are sending spacecrafts to Moon, Mars, Jupiter, and other planets. And we know that they have fuel cells, of course, they have special batteries, and they also have solar panels. So we know that recently another rover was sent to Mars, so it is also solar powered. So you can calculate using this relation the solar constant for Mars also. So 1367 watt per meter square is available outside the Earth's atmosphere. Please remember that this value is not received on the Earth's surface. Rather, this is received outside the atmosphere. We have not taken into account the atmospheric absorption till now. Okay, so likewise, you can calculate the solar constant for various other planets. For example, the spacecraft Juno. So Juno was a spacecraft sent by NASA for observation of Jupiter and its moons. So Juno was a completely solar powered mission. So it had a huge solar panel, but since the amount of energy that is received near Jupiter, that is significantly less than the energy that you get here on Earth or, for example, Mars. So the solar panels have to be designed in such a way that they are always facing the sun, their area is large, and the highest efficiency cells were used. So this radiation that you get outside the atmosphere, this is known as the extraterrestrial radiation or the AM0 radiation. Please note down this term, AM0. AM basically stands here for air mass. Air mass 0 basically means the radiation is not passing through any atmosphere. Radiation is not passing through any air mass. So AM0 radiation for Earth is 1367 watt per meter square, and for Mars it is 445 watt per meter square. And using this particular approach that we have shown, you can calculate solar constant for all the heavenly bodies, all the planets in our solar system. But beyond Jupiter, the radiation is very, very less, and some other forms of energy have to be used by onboard batteries or fuel cells. Okay. Now, let us see this term air mass, because this is a very important term. So whenever we are characterizing our devices, so there has to be some standard. So in standard testing conditions, you will observe that a term air mass 1.5 is used. Okay, so let us see about this, the term air mass. Okay, So I hope it is visible or you can see. So this is, here we have written air mass. So if sun is at zenith, that is directly overhead, this position zenith, zenith means directly over our heads. So, and this is our atmosphere, which we have shown. So the radiation that you get here outside the atmosphere, it is the AM0, air mass 0 radiation. So if sun is directly 90 degree above our head, this thickness of atmosphere, you can say, is exactly one unit. So for example, we say that the thickness of our atmosphere is a 200 kilometer. So this factor 1 basically means the radiation is going through or passing through exactly equal to the thickness of our atmosphere. Okay. But now, suppose the sun is not overhead, but it is at some angle, which is mostly the case in almost all the locations. Sun is directly overhead for a very short duration, short time in a given year, for only some days. And that too for locations which are within the Tropic of Cancer and Tropic of Capricorn, plus minus 23.45 degrees. The locations lying within these latitudes, they only will have sun overhead for some time during the year. Otherwise, for other locations, north and south, you will never have sun directly overhead. For example, in Raipur, you do have sun overhead for some times during the year, but for Delhi or for Srinagar, the sun will never be at the zenith position. This is due to the Earth-Sun geometry. Okay, so for an observer who is standing here at this point, if the sun is not directly overhead, it is making some angle with the zenith. Let me call this angle as theta z. So this is theta z, theta subscript z. Okay, so now just observe, this radiation is now passing through a greater distance because the path length has increased because of the angle of the sun. So due to this increased path length, what is happening? The radiation is being scattered away. So we all have studied that why the sky is blue, because the short wavelength, the blue wavelength, is scattered the most. It depends on inversely on the fourth power of lambda. Okay, so effectively, more radiation is scattered, more radiation is absorbed. Okay, so if your angle theta is changing, the amount of radiation that you are getting on the Earth's surface, that will change. You can think of it in this fashion also. The amount, the जो धूप आपको लगती है दोपहर को और सुबह और शाम को लगती है, उसमें बहुत फर्क होता है. Why is that? Because in morning and evening, so during morning time, you can see that sun is almost at this location. The radiation is passing through a greater path length of the atmosphere. So the absorption and scattering is very large. So in the morning and evening, the sun appears to be slightly orange in color, reddish or orange in color, and the amount of radiation that you are getting is significantly less what you get during the afternoon or during daytime. Okay, so to take into account these effects, this concept of air mass has been developed. So suppose we have a installation, a solar PV or solar thermal installation in Raipur, and another installation is in, say, Srinagar. So how do you compare? So basically, some standards have been developed. So this air mass 1.5, air mass 1.5 basically corresponds to an angle of 48.2 degrees. Okay, so air mass 1.5 corresponds to an angle of 48 degrees from the overhead position, and it turns out the solar radiation or irradiance corresponding to this position of the sun is 1000 watt per meter square. So this is a very good value for comparison, 1000 watt per meter square. And all over the world, if you are characterizing your solar thermal system or if you are characterizing your solar cells, this standard condition of AM 1.5 corresponding to 1000 watt per meter square is used. Okay. So, so I would request that if there are any questions, you can ask in between also. So no need to wait till the end. So you can type in the chat box if there are any questions. So this is another illustration of the air mass concept. This surface area here, if you talk about the surface area just outside the Earth's atmosphere, so all these surface areas are similar. But due to the curvature of the Earth, so suppose you are everywhere you are getting 1367 or 1370 watt per meter square. But that same power is now, due to the curvature of the Earth, it is distributed over a larger area. So at equator, you will get a higher value of radiation per meter square. But if you go very north or very south of the equator, the amount of energy or the amount of radiation per unit area, per square meter, that will be less. So it is quite obvious, due to the curvature of the Earth, the surface area has increased and the radiation that you are getting per meter square has decreased. Okay, so the first case is winter, when we have winters in North Hemisphere. And this case, middle case, is the equinox. Equinox basically means day and night lengths are equal in both the hemispheres. So that happens, we all know, on 21 March and 21 September. And of course, the summertime, so on 21st June, on the International Day of Yoga, basically, so you have the largest day, longest day. Okay, so we observe here that the North Pole is tilted towards the sun. So I would just like to remind the fact that change of seasons is because of tilting of the Earth's axis, not because of the Earth-Sun distance. There is no significant change in the distance of Earth and Sun to bring about climate change, but the climate is changing or the weather changes because of the tilting of Earth's axis. Okay. Yes, please raise questions using chat box. If there are any questions, I'll be happy to answer if I can. Okay, so like if someone is living in Kashmir or someone is living in very extreme north areas near to the poles, like in North America, Canada, or say extreme south of South America, Russia. So for those cases, even AM2, this particular value is also useful. So as the air mass is increasing, you just observe the value of the amount of available radiation is going down. Okay. So I can see that right now there are no questions in the chat box. So let us proceed further. Okay. So India is blessed with huge amounts of sunshine. So you can observe right from Kashmir to Kanyakumari and from Gujarat, Rajasthan to Northeast, our country's solar radiation is more than 4.5 or 5 kilowatt hour per meter square. Okay, so this is these values that you see. So here these are the daily average values. So we know that the 1 unit of electricity is basically 1 kilowatt hour. So almost all parts of India are getting more than 4 units on a daily basis, and that too on a meter square area, per meter square area. If you talk about annual values, almost all parts of India are getting more than 1,600 units or kilowatt hour per unit area, per meter square. Talking about total value, more than 5,000 trillion kilowatt hour per year are incident. So this is a huge amount of energy. You just see what is your electricity consumption, our household electricity consumption. How many units? 500 units or maximum 1,000 units? Or say if you are using more than one AC or some 2-3 motors, then you will get maybe say 2,000, 3,000 units monthly electricity consumption. So this is a huge amount of radiation that we are getting in our country, and it is therefore natural that we should look forward to utilizing this energy. Now, the first problem in installing any solar thermal or solar PV system is, for any given location, you want to know what is the available energy. How much energy is available. This is a map, that is okay. But for any given location whose latitude and longitude are known to you, if you talk how we can estimate the available amount of energy, so there are various methods. One is, professionally, what is done is people use some existing software like PVSYST or other tools like PVGIS, etc. And you just feed in the location and you can calculate the available energy. But what is actually the procedure behind that? How using pen and paper, basically you can calculate the available energy at any given location. So this is a very famous method of estimation of solar radiation empirically for a given location. So this is famously known as the AP equation or the Angstrom-Prescott equation. So equation is very simple. The first equation that we have written, the Angstrom-Prescott equation, this is very simple. You just have some constants and some values which are required to be found out. So here the A and B, these are basically some constants or coefficients which are constant for a given location. So ideally, long-term measurements of solar radiation have to be performed, and then only using curve fitting you can find out the A and B location, A and B coefficients. But fortunately for us, A and B coefficients for major cities in India are already available. And if you are in the same geographical area as that Indian city, you can use the A and B coefficients for that same city for your own calculations. Okay, now in this particular case, first we have to find out the value of HO, which we have done here. This is the monthly average extraterrestrial solar radiation. So it depends on the value that you have just found out, 1367 watt per meter square. Okay, and HGA, the monthly average daily global radiation on horizontal surface, is our parameter of interest. So HGA is what we want to find out, because HO, the extraterrestrial radiation, is basically same. Like if I talk about 27th June, so extraterrestrial radiation everywhere on the earth outside the atmosphere, that is going to be same. But taking into account the location, that is the main part. So we need to take into account the location. And location is accounted for by various factors. So phi, this phi is the latitude of your location. Omega S is the hour angle or sunrise hour angle. Delta is your declination. So what do these terms mean? We'll shortly see, but I would request that all of you can just quickly note down these two equations. Okay, so I hope you guys have noted down these two equations that we have. Let us proceed. Okay, so as I told, this is not an exhaustive list. A and B coefficients for other locations, other big cities are also available. But this is just to give you an idea that from north to south and east to west, for various cities, these A and B coefficients are already available. So like if I want to find out the radiation available in Raipur, I can choose Nagpur, because Nagpur and Raipur have almost the same latitude. And if you talk weather-wise, Nagpur is slightly more drier, but Raipur is getting, say, some more rainfall. But since I don't find any other place closer to Raipur, other places are very far away. And I don't want to use a location which is very near to the coast, because we are not having a coastal climate. Okay, so I can choose the coefficients used for Nagpur. So you can note down the coefficients which are there for Nagpur: 0.27 and 0.50. Okay, now let us proceed. So this is a simple problem. What you want to do is you want to estimate the monthly average daily global radiation on a horizontal surface in Raipur. So Raipur's coordinates. So these are the coordinates for IIT Bhilai's location that I have chosen. You are free to choose any location in India or any location on the globe. That is totally your choice. But the main problem is near to that location, for some big city or some already existing data, you should know the A and B coefficients. Okay. During the month of March, if the average sunshine hours per day are 9.2. So one thing is day length. From sunrise to sunset, what is the day length? That factor is the S max factor here. So S max is basically telling you the maximum number of sunshine hours. So maximum number of sunshine that you can get is basically from sunrise to sunset. But actually,
Dr. Nikhilji,
yes,
you are giving very nice presentation. Basically, I would like to speak to the participant. All the participants kindly note down such questions. And Dr. Mohammed is requested kindly, you may also put these questions during the evaluation test. So such kind of exercise can also be done after the completion of the session by the participant.
Surely, sir.
Okay, so you can note down such very important question being given by Dr. Nikhilji, and he is nicely elaborating all the aspect of the solar radiation.
Yes, sir.
And I am watching that many of the participants are, no participants are interacting with the speaker. And the speaker is from such a renowned institution, IIT Bhilai. So I would like to request to all the participants. Dr. Nikhilji, I am Dr. R.N. Khare, principal from University Bhilai.
Yeah. Good morning.
Good morning, sir. Good morning. Your director is also a governing body member of our Techniversity in Executive Council.
Yes.
So welcome you, sir, and sorry for interruption. And I would again request to all the participants kindly interact with the speaker, because the speaker is giving very good knowledge in this solar radiation aspect. Okay, thank you, sir. Please proceed.
Okay, thank you, Dr. Khare. So first I will answer some questions. Mr. Vishwajit and Mr. Ritesh have asked some questions. Does the solar radiation pattern in India demands for multiple time zones? See, if you consider the time difference between northeastern states and Gujarat, Rajasthan, yes, the difference in time is there. More than 1 hour difference is there, almost 1.5 hours. But that choice is totally government's choice. So as researchers, we can't say anything in that. But yes, all the, like for example, in Northeast, if the Delhi's office timing is say 9 to 5, then in Northeast, what they do, they start it from 7:30 to say 4. So that type of adjustment is being done by local administrators. But yes, whenever we are dealing with solar radiation, even a small difference, even a half-hour difference can actually result in several megawatts of power gain or power losses. So for any given location, I don't have much experience in the transmission sector, the grid lines, but I think Power Grid and other transmission companies, they do take care of the time difference between different locations of India. So that is all I can say about question by Mr. Vishwajit. And Mr. Ritesh, Mr. Ritesh, you are talking about the elliptical orbit. So if you just let me just show you the difference. Yes. So I think the slides are visible here. So the minimum distance is 147 million kilometer and the maximum is 152 million kilometer. So although our orbit is elliptical, it is not such an ellipse that I can't take this mean value for radiation distribution. And to account for this elliptical orbit of the Earth, I'm just going to explain you this. This factor is chosen. So n here is the number of days. N is equal to take care of the
Nikhil sir, it is not audible, sir.
okay.
Sir, it is, your voice is missing, sir.
Now is
Your voice is breaking, sir.
मेरे में सर रिकनेक्ट हो जाएगी दोबारा सर कोई इशू
now is it, now am I audible?
Yes, sir. Yes, sir.
Okay, I think there was some network issue here. Okay, so all right. I hope the slides are visible and I am audible.
Yes, sir.
Okay, so I was getting some background noise, so I would request that please mute yourself. I was getting some background noise, so it will disturb other participants. Okay. So Mr. Ritesh had asked for the elliptical orbit of the Earth. So that elliptical orbit part has been taken care of here. This particular factor here, 1 plus 0.033 cos of 360 n by 365. So this n is 1 for 1st January and n is 365 for 31st December. So we are assuming a 365-day year, not counting the leap years basically. It will take care of the elliptical orbit. Okay.
Okay, sir. Sir, actually,
All
I
right.
was asking about solar constant calculation. While solar constant calculation,
Yes,
we
yes.
have taken spherical surface. That is my problem.
Yes, so that is just an average value you have calculated. But when we are actually doing this detailed calculation, this S factor 1367, it will be multiplied by this particular factor. So it will slightly increase and slightly decrease. depending on the Earth's orbit.
Okay, sir. Okay, no problem, sir.
If it is at a farthest point, it will be slightly less. If it is at its nearest point, it will be slightly more. Okay. First thing. So we are doing this calculation for the month of March, and we are assuming that average sunshine hours per day are 9.2. See, this average value you can get from the meteorological database. If you just do a Google search, that is, say for example, average sunshine hours in the month of April for Jagdalpur. So you will basically get that value. So there are various online meteorological databases from where you can get this particular value. So I have similarly chosen this value to be 9.2 hours. So this is a long-term average. And since I am interested in the month of March, so let me take the middle of month to be 16th March. So you can take it 15th also, you can take it 16th also, but I think 16th is more suitable because you have 15 days before and 15 days after this. So being a 31-day month. Likewise, if you want to do it for say April, you can take 15th April as the day. So the value of N is 75 for 16th March. So you can do these calculations on your own. Now we come to declination angle. So this is the relation that is available for declination angle. And for 16th March, my declination angle is minus 2.41 degrees. What is declination? See, if you join the line, which line? From the center of Earth to the center of the sun, and take its projection on the equatorial plane, you get the declination angle. So we have shown here. So it is difficult to show such illustrations on a two-dimensional screen, but you just assume that Earth being a sphere. So Earth being a sphere, this is the equatorial plane. So it is coming out of the screen and going beyond the screen also. So this is the equatorial plane, and sun rays are coming from one particular direction. So on this equatorial plane, this particular angle that you are getting, this is the declination angle. So from 21st December to 21st June, the angle will change, and again from 21st June to 21st September, due to the tilting of Earth's axis, the declination angle will change. So this variation of declination angle is taken into account by factor N here. I would request that you, using just this simple calculation, you calculate the value of declination angle for today's date also, 27th June. Since 27th June is very close to the 21st June, the summer solstice, so you will observe that your delta value is almost what is written here, 23.3 degrees only. So this is going to be your delta value for today's date, 27th June. Okay. So I hope you know the concept of declination angle and you know the concept of delta here. Okay. Now again, if someone was wondering how basically in various apps or in normal calculations, normal astronomical or for our various calendar calculations, how we can find out the day length for any given day. This is how you can find out the day length. For your location, you can find out the day length for all 365 days of the year. How? This is the simple relation. Sunshine hour angle omega s. So it is equal to cos inverse. So basically all the calculations that you find in various panchangs. So they say ki astrologers are capable of predicting sunrise, sunset. So when is the lunar eclipse, when is solar eclipse? So those are not basically astrological calculations. Rather, they are well-established astronomical and trigonometrical calculations. Okay, so if we have knowledge of the relations, we can also tell about the different events. So right now, the only parameter of concern for us is finding out the day length. So you can use your location, that is your latitude, and you can use the delta value. And just by doing this simple calculation, you can find out the value of sunshine hour angle. Okay, and the day length can then simply be obtained in hours as you multiply your omega s, which you have obtained in degrees, you multiply it by 2 by 15. I hope, just let me explain why we have got this 15 factor here. So Earth rotates 360 degrees in 24 hours. So if I just divide this, I get that in 1 hour, the rotation is 15 degrees. So to account for this fact, I have taken this factor 15 here. And why I am multiplying it by 2? Because from sunrise to noon point, that is when sun is directly overhead, this is this particular angle. So if I want to calculate day length, basically I have considered for the noon to sunset, that part also. Okay, so you have calculated this particular angle. So you just, due to symmetry, the sunrise and sunset angles are same. So you can just multiply this by omega s by 2 to get the entire day length. Now just observe the dependence of day length. On 27th June, if you carefully observe, it depends on phi. So if you are in Jagdalpur, which is the south part of Chhattisgarh, and if say you are in Ambikapur, which is the north part of Chhattisgarh, there will be a difference in the day length. आपका जो day length है sunrise से लेके sunset तक का, वो जगदलपुर में और अंबिकापुर में same नहीं होगा. And this difference is even more during winters. So if you talk about 21st December, when sun is at its southernmost point relative to us. So for that day, for that 21st December, the difference in day length for Kanyakumari and the Srinagar, it can vary much. So just by noting down this particular relation, you can do all sorts of calculation. आप कैलकुलेशन कर सकते हैं, अपने होम टाउन के लिए कर सकते हैं, या फिर किसी भी वर्ल्ड की किसी भी लोकेशन के लिए आप कर सकते हैं. First, find out the declination angle, location, latitude you already know, and just by doing this simple trigonometrical calculation, you can find out the day. So for example, this is for 16th March. The day length is 11.87 hours. So I have done some calculation for today's date also. So for 27th June, that is today, the day length is for Raipur is 3.2 hours approximately. Okay. So if you take today's date, so the day length for Raipur is turning out to be almost 13.2 hours approximately. Okay, so in this fashion, you can actually find out the day length value. It's very easy. Now, going forward, so we are already running short of time and I have some more topics to cover. So, but I hope now you have got the idea how to perform this calculation. Now just in the same formula for H0, you can put all the values. So this H0 will be, H0 will have units of energy per meter square, watt hours meter square. Okay, so the main thing that you should know here is this omega S value is radians here. At least other values are in degrees, but in this relation, this here it is being my sine phi delta. So this is in radians. So this is the only thing that you should take care of. Otherwise, it is just a simple trigonometric calculation. So it turns out the H0 value is these many kilojoules per meter square per day. Now we are almost done with our calculation. So we are required to find out the value of HGA. I have found out HOA. A is known to me, B is known to me, S max you have calculated for your location, the day length, and SA you can find out from online databases. Okay, from meteorological databases, doing a simple Google search. Then my HGA value is calculated. Okay, so the average monthly global radiation falling on a horizontal surface in the month of March for Raipur is this much, 22,670 kilojoules per meter square per day. You can do this calculation for any location on the globe. Don't just say I don't have access to some special software and I cannot do it. Yes, you can do it. You just need few equations. The knowledge of A and B coefficients are required. And you can take the A coefficient, which is for a location which is nearest to you. Like if someone is from Chennai, for location for Chennai, A and B coefficients for Chennai are available. If someone is say in the same climatic zone, so they can take the A and B coefficient values for Chennai. But yes, a person living in Srinagar, he cannot take A and B coefficients for, say, example, Nagpur or Chennai. So those things you should take care of. Okay, so I think I have been able to make my point here, and let me. Okay. All right. Okay, so with this we finish the discussion on solar radiation. So my main aim telling you about solar radiation was that most of us only talk about solar thermal and solar photovoltaics, that this much power has been generated, that much has been generated. But first of all, we should be aware about how much energy is solar energy is actually available on your location. And please don't depend on any software, etc. You can just do your own. And this particular calculation is quite accurate. Yes, I acknowledge that the model has limitations. There may be some error, but at least this will give you a good starting point to start designing your own system. So you know that for your location, it can be your village, your hometown, whatever, that this much energy is available. Then based upon this, you can go further. Okay, so I have to show some more slides quickly. So this is how solar radiation measurements are done actually. So you have pyranometer and pyrheliometer. So it measures the global and diffused radiation, and this has a tube. So only direct radiation from sun is going here. So it will measure the direct solar radiation. So this is parameter is installed at IIT Bhilai, and we are recording the data from sunrise to sunset. So we have made this system. Mr. Shravan from BIT Raipur, faculty at BIT Raipur, so he has also helped us in installing this system and developing the complete data logger. So, okay, let us quickly go through some basic concepts of solar photovoltaics. So what is photovoltaic effect? Generation of photovoltage due to light incident on a PN junction. In simple words, this is the photovoltaic effect. It was experimentally observed or demonstrated by Edmund Becquerel in 1839, but it took more than 100 years to actually make a practical cell. So in 1954, the first practical solar cell was demonstrated by these three engineers whose names are given here. In between, there were some experiments, but they were not very useful. But yes, they helped in improvement of understanding of the physics. 54 marks the year in which a practical photovoltaic cell based on silicon was demonstrated at Bell Laboratories. Okay, so those of you who want to have the exact definition of photovoltaic effect. So basically, when light is incident on a PN junction, due to buildup of positive and negative charges, a potential difference is built up. And since this voltage is built up due to incident photons, the effect is known as photovoltaic effect. So this is the IV curve of a solar cell. Now you must be wondering why I have shown the IV curve to be in the fourth quadrant. So this is the quadrant we all know, first, second, third, and fourth. So if you observe carefully, as per the convention, solar is giving you negative current and the voltage is positive. So your power is effectively negative. A negative power basically means that your device is basically generating power, it's not consuming power. So this is the curve of a diode. So diode works in the first quadrant. So the product of I into V is positive. So basically we know that all electronic devices are power consuming devices. Then for solar, we are getting this power to be negative. It means that you are generating power. So please remember, solar cell operation is in the fourth quadrant of IV curve if you take IV curve. But for ease of visualization, इसको आसान तरीके से दिखाने के लिए, we normally show it in the first quadrant. But please always remember, basically you are dealing with the first quadrant operation. Okay, so this is what I was talking about. Just for ease of visualization, we are showing it in the first quadrant. So you have basically two main parameters, the open circuit voltage VOC and the short circuit current ISC. So if you know the area of the cell, you can divide short circuit current by the area and talk about current density also. Now please understand that short circuit current and the open circuit voltage are the theoretically maximum voltage you can get. If you operate at your solar cell at VOC point, the current is zero, so the power is zero. Likewise, if you operate your solar cell at short circuit point, the current is maximum, but the voltage is zero. So again, your power is zero. So we want actual power from the solar cell. That is why solar cell is operated at some point known as the maximum power point. So corresponding to this maximum power point, you have the value of Im and Vm, Emax value and Imax values. Okay, we have the term known as fill factor, FILL, fill factor, which is given as a ratio of maximum power is Vmax Imax divided by Vc Isc. So sometimes you will see that the curve is like this. This is not a good solar cell because the factor is less. I would like my solar or solar photovoltaic module to display a very square figure, as square as possible. Okay, and of course, the efficiency of any device we know. Okay, so the efficiency of the device is the power generated, the Pmax, divided by the incident radiation, the power of the incident radiation. So normally, as we have seen, AM 1.5 corresponding to 1000 watt per meter square or 100 milliwatt per centimeter square, that is considered as the incident value. And we get this simple equation of efficiency. So if you want to calculate efficiency, just VOC into ISC into fill factor. This denominator will anyways be 100 milliwatt per centimeter square. So just by multiplying these three terms, you can get the efficiency. I'll just show an example. So before that, this is the electrical equivalent model of a solar cell. So electrical engineers are mostly interested in this because they can do some modeling. They can find out various parameters. For this current for diodes, this is normally not known. So by measuring the IV curve of a module, they can, using various modeling techniques and using various software like MATLAB, they can find out this value of J0. Or like, for example, even the ideality factor is considered to be 1 here. So sometimes the ideality factor is also not 1. So this J0 and N values can be calculated by doing this modeling. So this is just for sake of completeness, this is the symbol of a solar cell. You just show the symbol of a battery, some positive and negative terminals, and close it in a circle and show that light is incident. So this is how solar cell can be shown in an electrical circuit. So this is some data that I have taken from my research. This is an example of a dye-sensitized solar cell, and we are showing the IV curve in first quadrant. So I got an ISC value of 11 milliamperes. Okay. So my active area was 0.64 centimeter square. So I can calculate my short circuit current density. 11 divided by 0.64, 17.2 milliampere per square centimeter. Fill factor that I got was 65.5%. Fill factor basically means the maximum power point. So corresponding to the ratio of VMIM by VOC ISC. And my measured VOC was 0.77 volts. So how can I calculate my efficiency? I'll just multiply my short circuit current density, fill factor, and voltage. See, so I get an efficiency of 8.67%. So you may ask, I have not divided by anything, because I have to divide by 100 milliwatt per centimeter square. And if I want to have in percentage, I have to multiply by 100. So basically these two factors are cancelling each other. So basically, if you are doing your measurements under standard testing conditions of 100 milliwatt per centimeter square, you just have to divide by, you just have to multiply these three factors and you will get your efficiency. However, if you know that your radiation is not 100 milliwatt per centimeter square, in that case, the denominator value will not be 100 and it will change. Okay, so we have to take care of these points while doing the measurements and calculations. So your evaluation, I can give a simple question, like the short circuit current is this much, fill factor is this much, the incident radiation is this much. Find out the efficiency. So please note down what is the denominator value. Is it 100 milliwatt per centimeter square or is it something else? Because see, nowadays in monsoon, the amount of available radiation is very less. So the current and voltage, everything that you are getting from your solar cell or solar module, that is going down. So the efficiency that you see for solar PV modules, that is only at STC. वो सिर्फ स्टैंडर्ड टेस्टिंग कंडीशन के लिए होती है, तो आप अपने मॉड्यूल्स के पीछे एफिशिएंसी देखते हैं. फॉर अदर रेडिएशन वैल्यूज यू हैव टू कैलकुलेट द एफिशिएंसी. Okay, so I'll just skip this part for the time being. I'll just want to show you this. So you must be wondering what are the different types of solar cells. So actually, there are tens of solar cells which are being developed nowadays. So this is a very famous chart. In all the presentations on solar cells, you will see this particular chart. This is from National Renewable Energy Laboratory, USA. So all the types of PV panels and solar cells and their best efficiency up to date. So like for example, this was updated in April 2021. So if you want to know what is the highest efficiency of a single crystal silicon solar cell, so it is here, 26.1%. 26.1% is the highest efficiency for a single crystal solar cell. Okay, so like my research area is in perovskite cells, perovskite solar cells. So perovskite solar cells, maximum efficiency achieved for perovskite solar cells is also very close to silicon, 25.5%. So some solar cells are used exclusively for space applications. They are multi-junction cells which have 3 junctions basically. So for multi-junction cells, if you observe, the efficiencies are of the order of 35-36%. Okay. And value they are seeing 47.1%. This is basically for concentrator solar cells. That is using special optical arrangement. Light is concentrated, sunlight is incident on the multi-junction cell. Okay. So if you ask what is the highest efficiency for a single junction cell, the answer would be the highest efficiency for a single junction cell is 26.1% for silicon solar cells. Okay, and if someone asks what is the maximum efficiency for solar cells in general, then you can say it is about 47% for multi-junction cell with concentrator optics. Okay, and anyways, you can just search the NREL chart and you can get this particular chart and you can see it in detail. Okay, so this is the general solar PV manufacturing process. You have quartz, basically sand, that is SiO2, and using various steps, you make cells, and by arranging cells in series, you make modules, and finally we have large-scale power systems. So this is the module structure. So time is short, so I have to basically quickly go through the slides. So this is the module structure. You have cells, and on top and back side, you have some EVA encapsulation. Okay, and then you have outer aluminum frame and glass, and basically at the outside you have a junction box. So these are the various types of modules which we have here at IIT Bhilai. So I have shown this photograph basically to show you that various sizes of modules are available. This is 50 watt peak. This is 80 watt peak. In between there is 150 watt peak, which we don't have. Then you have big panels, 330 or 370 watt peak. And also you can see there is a difference in color. This is slightly bluish in color. This is slightly grayish or blackish in color. This is polycrystalline. This is monocrystalline. How to identify polycrystalline and monocrystalline? Let us see. So this polycrystalline solar cells are mostly स्क्वायर इन शेप. ये पूरे स्क्वायर होते हैं शेप में और थोड़ा ब्लूइश कलर होता है इनका. द मोनोक्रिस्टलाइन सोलर सेल्स आर नॉट परफेक्टली स्क्वायर. आप देख सकते हैं थोड़ा एजेस के ऊपर ये कट मिलेगा आपको, एंड दे आर डार्कर, दे आर ब्लैकिश. सो दीज आर मोनोक्रिस्टलाइन सेल्स. ये ऐसा क्यों होता है ये फिर कभी डिस्कस करेंगे, बट दिस इज जस्ट टू गिव यू अ जनरल आइडिया हाउ टू आइडेंटिफाई बिटवीन पोली एंड मोनोक्रिस्टलाइन. So just by looking at this, you can say, yes, this is monocrystalline and this is polycrystalline. Okay, so this is poly, this is mono. Nowadays, bifacial modules are available. So they can absorb from front side as well as back side. Okay, so we also have these modules at IIT Bhilai. Okay, I have the standards. There are some standards for PV modules. Okay, let us see some applications. Largest solar plant in India and the world. We should be proud to know that the largest operational solar PV plant is in India. पहले चाइना में था, हमने चाइना को हरा दिया. It is in Jodhpur district, Rajasthan. 2250 megawatt. आप देखिए. Just observe. These satellite images are showing how the plant was constructed over a period of 4 or 5 years. So it is covering several square kilometers, and you can observe that the modules that are being used, they are mostly polycrystalline. The difference is monocrystalline module is giving you a higher efficiency, but its cost is also higher. Say, so for example, if one monocrystalline and one polycrystalline module, the cost difference is about 2000 rupees. So if you are procuring in bulk, maybe the cost difference is 1000 rupees. But suppose you are installing 10 million modules. If you have to multiply 10 million by 10 rupees, so you have to pay significantly higher amount for monocrystalline modules. So a cost factor is actually limiting the growth of monocrystalline technology, because any big installer, big manufacturer, so they will see that if I have to sell 10 million modules, the user may not be interested in buying monocrystalline. So this big solar park that you see, it is made up of polycrystalline modules. And I must tell you, when I am saying that this 2.2 gigawatt solar power plant, it is not having a single power station. So basically there are several different parts, one part 100 megawatt, another part 70 megawatt. So in that case, for 6-7 different utility operators are basically extracting power from this solar power plant. So one utility is not directly getting power from this complete solar plant. Okay, but yes, this is the largest installation in the world, 2.2 gigawatt, and more such plants, ultra mega plants are coming up in India. देखिए कितना सैटेलाइट से इमेज लिया हुआ, कितना बड़ा एरिया है ये, and that is why this in Rajasthan is highly suitable for installation of big solar plants. And you will be surprised that in the bidding process which was conducted by Solar Energy Corporation of India, जो ACME Solar Holding Limited, this company had quoted a final tariff of 2.44 rupees per unit. आप देखिए, you are paying maybe 5 or 6 rupees per unit for the conventional electricity. So now we can safely say that solar PV power has achieved grid parity. When we say grid parity, it basically means that the cost is now at par with the conventional thermal power or conventional hydro power. Okay, so the future looks very bright for solar PV, and we can expect even further lowering of the cost. Yes, floating solar power plants are also there. किसी भी लेक के ऊपर, किसी भी वाटर बॉडी के ऊपर यू कैन हैव फ्लोटिंग सोलर प्लांट्स. इट हैज ए ह्यूज एडवांटेज. सबसे बड़ी एडवांटेज ये है कि यहाँ पे कोई लैंड के लिए लड़ाई झगड़ा नहीं है. देयर आर नो लैंड इश्यूज. ओके, एंड these modules, they operate at a lower temperature. They prevent the evaporation of water. So they are very helpful from water conservation point of view. Okay, there is no shading. कोई भी यहाँ पे पेड़ वगैरह नहीं है आसपास, तो इन पे कहीं भी शेडिंग नहीं है. ये दो एग्जांपल्स हम दिखा रहे हैं. 450 किलोवाट पीक इज देयर एट कोचीन एयरपोर्ट, एंड ए वेरी बिग 14.7 मेगावाट पीक इज देयर इन तमिलनाडु, Southern Petrochemical Industries. So they have their own captive ponds for some use, and they have installed such a huge capacity of floating power plants. So floating power plants, you will see more and more floating power plants will come. Chhattisgarh is sort of potential for floating power plants. यहाँ पे इतने ज्यादा तालाब, इतने ज्यादा नदियां, इतने ज्यादा ponds हैं, उनके ऊपर हम रख सकते हैं. Imagine विवेकानंद सरोवर रायपुर में है, उसका बहुत बड़ा एरिया है. वहां पे आराम से several hundreds of kilowatt peak of solar floating plants can be set up very easily. This is an example of Switzerland, 448 kilowatt peak of floating power plant. So there are some, of course, some advantages.
Excuse me,
of
sir.
course,
Hello.
Space applications are there for. Yes.
Sir, I have a question.
Yeah.
Sir, first of all, thanks for this good, very nice and excellent presentation. I would like to ask, sir, if we can install this on river, or means on water body, why don't we install on the stations? And most of the government were rooftop, and since railway covering most of the area, land area, can we install on the rooftop of train? The train which
Yes,
is
yes.
going long distance, like from Delhi to Cochin, Kerala Express, and Bharat Express from Delhi to Kanyakumari, means the long distance train traveling and exposing most of the time to the direct radiation of solar. So does the installation is beneficial for long time, or it will be a means just non-profit expense?
See, if you talk about the surface area available over trains, that is large. Okay, so all the electrical items in the train, like for example phone chargers and lights and fans, they can be operated. But I think operation of ACs will not be possible with that area, and the electricity budget of the railway network can definitely be reduced. But till now, the modules are not as efficient that if we install the modules completely on a train, it will be able to power the whole train. That is not possible now. So maybe that is one reason why railways are not considering it actively. But yes, railway buildings in most stations you will see that they have already installed solar rooftop. For trains and other vehicles like buses, we may have to wait for some more time when the modules are more efficient and the loads that we are using, their power consumption has been reduced, then we can consider going for solar. But I will have actually using solar power. Yes,
Sir, yeah, when we are now entering in the age of automobile running by electricity, so it is the very need of high amount of electricity for running automobiles. So can this automobile can also be?
Yes. Yes, definitely. So what you will see in near future is there will be solar powered charging stations, just like we have now. We'll be able to charge our car in say 5 minutes or 10 minutes. The technology will become advanced to that level. However, for the completely solar powered car, we may have to wait say maybe another decade or so. So research is being done in that direction that we get. So it is a multidisciplinary thing. You need to have good quality motors also with very, very low losses, and you need to optimize your material so that the weight of your car is less, and likewise so many things. So yes, definitely you will see more and more solar coming up and more solar in our energy mix. And this so 10 years later, or our children, they will buy basically an electric car which will be charged by solar panels. Yes, that's the reality. And in many parts of the world, technology demonstrations have already occurred. But in India, for commercial level, we may have to wait for some more years.
Good morning, sir.
Yeah, good morning.
Thank you, sir. Thank you.
Sir, you have visited to our college and you have seen our solar panel
Yes.
of 130 kVA. So many panels are damaged.
Yes.
And
Yes.
what we have to do to replace, means it requires money, but what we can do for waste utilization, because solar panels should be replaced as per your guidance or advice within 5 to 7 years, because no any technology is available for its longer life.
No. Actually, if we talk about polycrystalline and monocrystalline panels, their life is more than 20 years.
Okay.
But due to some accident or some electrical failure,
Lightning and other.
they may have to be replaced.
Okay. And how we can convert it to waste to money? Means waste utilization, how we can do it?
Yes, so that's a very good question. In fact, this is again an area of ongoing research, and unfortunately, India is not paying attention at the moment. So this may be considered as an active area of research in near future, because now we are starting to get electronic waste, especially the modules installed 20 to 30 years back. And now they are basically acting as a waste. So the glass, the silicon, the silver, and other metal parts which are used, so they may have to be, what we say, recycled.
Okay, sir. Because
So
the
one thing
glasses
is,
can be
one major area of research. One major area of research for silicon is, like if silicon solar cells have served their lifetime, they can serve as a feedstock for making fresh silicon wafers.
okay.
Okay.
Glasses
And
can
regarding
also be
glass is a very
recycled for
tricky thing, because
मिश्रा जी, निखिल साहब को कंप्लीट कर लेने दीजिए अपना लेक्चर को.
सर
उसके बाद फिर और फॉर मोर क्वेश्चंस यू में पर्सनली आस्क थ्रू मेल. ओके, so that more participants may interact. Please conclude your presentation, sir, Dr. Nikhil ji.
So I just wanted to show one case study of rooftop application. So it is not as if I am just teaching and talking about solar. So we have also to use solar in our home. So my hometown is in Vienna. So this is just a photograph of the system that we have. So I have there 160 watt peak modules, 2 in numbers, and then commercially available solar inverter. So these solar inverters are also known as power conditioning units. And I think most of the people who are listening to this presentation, they may already have an installed inverter and battery backup system in their households. So how can you go solar without spending much? Just a small investment is required. Battery is the costliest item in balance of systems. If battery is already available at your home, you just need to buy a solar panel and a solar inverter. Let's do some cost analysis. 160 watt peak modules. So their cost is roughly about 26 rupees per watt peak. So those of you who don't know, just you go and buy other items in rupees per kg or rupees per dozen. For PV modules also, the cost is calculated as this many rupees per watt peak. So this is just a cost 26 per watt peak that is nowadays commonly available in Indian market. अगर कोई आपको इससे ज्यादा पे दे रहा है तो उससे बार्गेन करो. It means कि he is making a huge profit. तो 25 से लेके 28 रुपए पर वाट पीक के बीच में मोर और लेस आइडियल कॉस्ट है आज की डेट में. आई एम टॉकिंग अबाउट रेजिडेंशियल यूजर्स, नॉट अबाउट big users like colleges or other big companies. Okay, so as an individual you can just go and bargain कि मेरे को 25 रुपए या 26 रुपए पर वाट पीक में आप दीजिए. Okay, so my total investment was 22,000 rupees, but this battery was already available, so that is why I have kept it in red color. This is my load that I am running: LEDs, TV and fan, and this is the hourly utilization of energy. So the morning to night equipment. So this is the profile. So in the evening time the loads are running as is in most. ठीक है. So this anyways I would like to tell you the simulation etc. I have done using this. So total loads that I have connected is 384 watt and the power handling capacity of my PCU is approximately 600 watt. Okay. And this is the loss diagram that I have. So the main point is just by spending 13,000 rupees, I am able to score 91 a year. So if I take the nominal cost to be rupees 7 per kilowatt hour, so my yearly savings is 400. So the average time in which I am getting my money back is about 6.5 years. However, if I don't consider the battery cost, the investment return time is 4 years only. So if you have a battery, what you need to do, just go and buy a solar inverter. अगर आप 1100 VA का या 1500 VA का इन्वर्टर यूज कर रहे हैं तो आप लगभग उसी कैपेसिटी का एक सोलर इन्वर्टर बाय कर लीजिए और चाहे आप सिर्फ एक ही उसके ऊपर पीवी पैनल लगा दीजिए. Immediately you start using solar. See, my missing energy is 76%. So ideally, as an engineer, if I have to design a system for full use of solar energy, many detailed calculations are required. But to make sure that you start using renewable energy, you start using solar energy immediately in your energy mix, the answer is very simple. एक सोलर इन्वर्टर या सोलर पावर कंडीशनिंग यूनिट लीजिए और चाहे तो सिर्फ एक ही मॉड्यूल क्यों ना लीजिए, इमीडिएटली आप सोलर एनर्जी को यूटिलाइज करना शुरू कर सकते हैं. ओके, अगर आपको लगता हो कि 10,000 रुपए या 15,000 रुपए और 20,000 रुपए बहुत ज्यादा कॉस्ट है, तो मैं आपसे एक क्वेश्चन पूछूंगा कि आप स्मार्टफोन जो यूज करते हैं उसकी कॉस्ट क्या है. आईफोन आता है तो हम सब भागने लगते हैं आईफोन लेने के लिए, OnePlus लेने के लिए. सो जस्ट द इन्वेस्टमेंट is very low. We can afford 20,000 rupees easily and immediately we can start using solar. And later on, year by year, you can just start increasing the number of modules that you have installed or the number of batteries that you have. Okay, so I would recommend that this is from my own experience. and I would recommend that all of us should start using solar as soon as possible. We should not wait for government policies, or we should not wait for others to do so. We ourselves should do so at the earliest. In fact, in our agricultural fields, we have this small room. It doesn't have any electricity connection. It is just powered by a 150 watt peak module. This is a common use case in most parts of our country, जहाँ पे कि खेतों के पास थोड़ी बहुत इलेक्ट्रिसिटी चाहिए. किस चीज के लिए चाहिए? लाइट, फैन और मोबाइल चार्जिंग. मोबाइल चार्जिंग तो अभी आ गया है, पहले नहीं था. इसके लिए आपको ये जो सिस्टम मैंने वहां पे इंस्टॉल किया है मेरे गांव में, खेत में, just 150 watt peak panel, LED bulbs, DC LED bulbs. These are not your common LED bulbs which you buy, which you insert in your socket for AC. No, DC LED bulbs are separate. You have some solar charge controller. उसकी एक फोटो मैंने यहाँ पे दिखा रखी है. It already has outlets for fan, lights, and USB port for charging. So the complete cost of this system was 9,500 rupees, including a DC fan. And it works nicely. It works nicely. It's a truly do-it-yourself project. आपको जस्ट मार्केट जाना है, 10,000 रुपए लेके आप ये सारी चीजें एक साथ खरीद के अपने घर में रख सकते हैं, या फिर ये कंप्लीटली ऑफ ग्रिड सिस्टम है. 10,000 रुपए से कम में यू स्टार्ट यूजिंग. उनका बहुत अच्छा है. दिस इज एडीसी फैन विच वर्क्स वेरी नाइसली. 2-3 लोगों के लिए बहुत सफिशिएंट है. You can easily use 2 LED bulbs and a phone charger, just like shown here. So it gives you 2 amperes. So 2 ampere, 5 volts. So 10 watt charger. So 10 watt charger is a very good charger. Okay. So that's all from my side. So normally people say go green, go solar. So I have just inverted it. Go solar, go green.
Thank you so much, sir.
Thank you, Terry. Thank you, sir, for very nice presentation, and you have covered all the points of utilization of the solar energy. Really, I am very thankful of above university that you have took out time in very busy schedule. Actually, जो अभी मैं सर का presentation देख रहा था, और अभी डॉक्टर मिश्रा जी ने भी बहुत अच्छा क्वेश्चन किया था कि जो खासतौर पर रिपेयर मेंटेनेंस के बारे में, क्योंकि इस पर जो डॉक्टर निखिल जी, मैंने भी बहुत काम किया है सोलर एनर्जी पे, और यहाँ छत्तीसगढ़ गवर्नमेंट से मैं उसका मेंबर भी था, सेम में सोसाइटी एनर्जी एनवायरमेंटल. उसमें यहाँ पर एक गुड़गांव में एमटेक के दौरान मैंने एक बिल्डिंग बनाई थी, नेचुरल एयर कंडीशनिंग बिल्डिंग. और उसके लिए उसमें क्या हो रहा था कि हाँ, नेचुरल एयर कंडीशनिंग बिल्डिंग, उसमें 4 मीटर डेप्थ पर टेम्परेचर थ्रू आउट द सीजन कांस्टेंट हो जाता है, और अर्थ एयर टनल पाइप सिस्टम के द्वारा उसमें 3 हॉर्स पावर का ब्लोअर हमने लगाया था इनलेट पे, और वो ब्लोअर जो है सक करता था एम्बिएंट एयर को, और 4 मीटर डेप्थ पर टेम्परेचर थ्रू आउट द सीजन वहाँ टनल के द्वारा टेम्परेचर रिड्यूस हो जाता था. ड्यूरिंग द पीक समर सीजन मान लो टेम्परेचर 47 डिग्री सेंटीग्रेड है, तो ब्लोअर जो है सक करता था और नीचे 4 मीटर डेप्थ से ले जाता था, एंड एट द आउटलेट वी आर गेटिंग 28 डिग्री सेंटीग्रेड. तो लोगों को कूल लगता था. ठंड में 8 डिग्री सेंटीग्रेड रहता था ड्यूरिंग पीक विंटर सीजन इन दिल्ली क्लाइमेट, स्पेशली गुड़गांव साइड. तो वो एम्बिएंट एयर को सक करता 8 डिग्री, फिर अगेन इंक्रीज हो जाता 28, क्योंकि नीचे जमीन के नीचे जो सोलर रेडिएशन की विशेषता होती है, जैसे जैसे वो सन पेनिट्रेट करता है तो वो जमीन में जैसे नीचे जाता है उसमें टेम्परेचर जो है कम होता जाता है, 47, 46, 44, और इस सर्टेन डेप्थ पर टेम्परेचर कांस्टेंट हो जाता है थ्रू आउट द सीजन. तो इट डिपेंड्स अपॉन द थर्मल कंडक्टिविटी ऑफ द सॉइल. तो उसमें देखा कि 4 मीटर डेप्थ पर थ्रू आउट द सीजन कांस्टेंट हो रहा है. वो टेक्नोलॉजी को यूज करते हुए बाद में उस बिल्डिंग को नेचुरल एयर कंडीशनिंग बिल्डिंग डिजाइन किया था. बहुत पुरानी बात है, जिस समय मैं एमटेक कर रहा था. IIT दिल्ली का भी उसमें हमारे को गाइड थे. एक बड़ी इंपॉर्टेंट चीज है जो पूरे प्रेजेंटेशन में मैं देख रहा था, डॉक्टर निखिल जी ने बहुत अच्छे प्रेजेंटेशन दिया. आज के समय की जो आवश्यकता है, जितनी भी चीजों में, वो समय की आवश्यकता ये है कि हम यूटिलाइजेशन ऑफ जो नॉन कन्वेंशनल एनर्जी सोर्सेस को ज्यादा यूज करें, ताकि कोविड जैसी बीमारियों से बच सके. अदरवाइज आदमी जिंदा ही नहीं रहेगा तो करेगा क्या भाई? आप कितना भी डेवलपमेंट कर लेंगे, और आज सोलर एनर्जी हम कहते हैं उसकी लाइफ क्यों ना 20 ईयर्स हो, लेकिन उसके बाद में हम लोग यदि हम नेचुरल एनर्जी रिसोर्सेज को यूज ना करके, और ये जो स्टील स्ट्रक्चर्स को जो बना रहे हैं, स्ट्रक्चर में चाहे सिविल हो चाहे मैकेनिकल हो, जो टेक्नोलॉजी को हम लोग यूज कर रहे हैं वो डेफिनेटली जो है वो हमारे नेचर को, ये एज को कम कर रही है और आदमी की एज को भी कम कर रही है, और कोरोना और कोविड जैसी बीमारियां जो है आ रही हैं। कई बार प्रेजेंटेशन में मैंने बोला कि बेसिकली जो कोविड जो है वो चमगादड़ में कई वर्षों से था, हजारों वर्षों से था। ऊंटों में जो है मार्स की बीमारी हजारों वर्षों से थी। उसके बाद एड्स जो था, ग्रीन अफ्रीका के जो बंदर थे, बंदर, वो उन बंदरों में हजारों वर्षों से था एड्स। लेकिन लोगों ने क्या किया, बंदरों को खाना शुरू कर दिया, सांपों को खाना शुरू कर दिया, चमगादड़ों को खाना, उनके फार्म हाउस बन रहे हैं चाइना में। तो उस केस में क्या हो रहा है, वो जीव जंतु जो उनके शरीर में थे वो मनुष्य में ट्रांसफर होना शुरू कर दिया कि उनके रहने के लिए कोई जगह मिली नहीं। तो उसी तरह से लोगों ने क्या किया, सोलर एनर्जी का यूटिलाइजेशन, विंड एनर्जी, जियोथर्मल एनर्जी, टाइडल एनर्जी, ओशन एनर्जी, बायोमास एनर्जी का यूटिलाइजेशन न करके जो इलेक्ट्रिफिकेशन के जरिए जो इस तरह से जनरेशन ऑफ इलेक्ट्रिसिटी किया या डिफरेंट यूटिलाइजेशन जो हम कर रहे हैं, उससे कहीं ना कहीं हम लोगों ने जीवन और आगे वाली जनरेशन का भविष्य अंधकार में कर दिया है। ये आज के वेबिनार का जो इम्पोर्टेंट सस्टेनेबल डेवलपमेंट है जो हमारे डॉक्टर मोहम्मद जी ने रखा है, बहुत ही रिलेवेंट टॉपिक है, उसको समझने की बहुत आवश्यकता है। पेबैक पीरियड में हम लोग देखते हैं इनिशियल कॉस्ट ऑफ इंस्टॉलेशन सोलर एनर्जी या विंड एनर्जी की बहुत ज्यादा रहती है। सोशल एक्सेप्टेबिलिटी बहुत पुअर है, पब्लिक जो है उसे एक एक्सेप्ट नहीं करना पड़ती, उसको एक मजाक का केंद्र बना लिया है। लेकिन आप देखेंगे आने वाले समय में जिस तरह से ये लोगों ने क्या किया, सारी चिकित्सा और मेडिकल साइंस और सब पर लोग चर्चा कर रहे हैं, लेकिन इस बात पर चर्चा नहीं हो रही कहीं पर भी कि बेसिकली ये कोविड किस कारण से आया है। ये तो मनुष्य का दिया हुआ है, तेरा तुझको अर्पण। तो बेसिकली यही इसका इम्पोर्टेंट है कि जो हम लोग यूटिलाइज, ज्यादा समय नहीं लूंगा मैं तो जस्ट ऐसे इंटरेक्ट कर रहा था। इतना रिलेवेंट टॉपिक है, खासतौर पे पूरा थीम जो हम लोगों ने, ये आईसीटी ने जो अप्रूवल दिया है, उन्हीं थीम को अप्रूवल दिया है जो कि न्यू एजुकेशन पॉलिसी के तहत इम्पोर्टेंट है और साथ ही भविष्य, आने वाले भविष्य के लिए बहुत इम्पोर्टेंट है। तो विथ ऑल दीज वर्ड्स आई एम वेरी मच थैंकफुल टू डॉक्टर निखिल जी, and few questions if we have participant may ask, and also requested to all the participants kindly take the email ID of Professor Nikhil ji, and you may also personally interact to save the time, because I want that every program and session will start at due schedule timing. Thank you, sir. Thank you very much.
Thank you, Dr. Khare, for the kind words. And yes, whatever Dr. Khare has said, that is very much relevant in present times. So we must not only talk about green energy, we should adopt it actively in our lifestyles. And any development, if it is not sustainable, it will lead to crises like the ones we are seeing nowadays. Okay, so please, we should try to be Atmanirbhar in case of our own energy needs also. So like one person, Mr. Chandrasekhar, I think he asked about the cost. So the benchmark cost of installing 1 kilowatt peak of solar power is about 45,000 rupees. But in my experience, if you just do your own survey, you can actually achieve it in 5 to 10,000 rupees less. So if someone is ready to spend 1 lakh rupees, in 1 lakh rupees, actually he can easily power a 2.5 kilowatt load in his house. That is very much possible nowadays. Okay. So, but yes, like I told, the calculations which I presented here, they were basically for an undersized system. So just immediately, if someone wants to use, they can immediately start using. But if you want to have a properly designed system, some detailed calculations will be required. But yes, from my experience, I can tell you in 1 lakh, you can easily install 2 to 2.5 kilowatt peak system. So I thank you once again to Mr. Dr. Khaja and BIT Raipur, Director, and Dr. Khare for giving me this opportunity. And I think whatever we have discussed here will be useful. So thank you. Thank you once again.
We are very much thankful, sir. As a part of the faculty development program, you have spared your valuable time from your busy schedule. For your participants, for your kind information, the expert Dr. Nikhil Chande has given his session on solar energy technologies and applications. He has shared a deep knowledge about solar radiation, solar photovoltaics, solar potential, as well as the scope of solar photovoltaic installation. He also shared about how we can have the sun radiation and other renewable energies available with us. He has beautifully explained the relation of science, technology, and the concept of Panchang in our day-to-day life with the relevant examples. He also showed the scope of the research available in the area of solar technology, and also given live expenses how we can utilize the solar technology without taking the help of electricity at a minimum cost. Thank you so much, sir, for giving our brief examples for our utilization in the day-to-day life. And once again, I thank the AICT CSVTU team for giving up this opportunity to host the program on green technology and sustainable engineering. Thank you, Nikhil sir, once again. For the participants, for the kind information, the FDP is completely focused on themes and sub-theme based, basically on energy, environment, sustainable energy, as well as the education policy with the relevant case study. So I advise all the participants with the renowned institutes to please come on time and participate on time so that you can have a beautiful concepts of technical oriented and get it to be implemented at your institute level towards the students. Thank you one and all.
ये डॉक्टर खाजा जी, ये जो पार्टिसिपेंट जो कम ज्यादा हो रहे हैं ना, जैसे अभी 49 है, पहले 65 थे, फिर 70 हो रहे हैं ना
सर,
तरह के जो पार्टिसिपेंट्स हैं जो कंप्लीट नहीं कर रहे हैं सेशन वगैरह बीच में आ जा रहे हैं ना
जी सर,
इसको थोड़ा वाच करेंगे, यदि वो 30 मिनट से ज्यादा होता है तो होल डे एब्सेंट माना जाएगा.
surely sir.
Some participants are on simply joining for getting the certificate. This is the AICT sponsored program. Okay, no participant will get certificate at any situation if he is not satisfying the condition of 80% attendance of all sessions, as including the 60% passing marks in this evaluation test. Because I am watching, because many of the participants simply joining and raising questions and quitting the session. Okay, this practice should not be accepted at all. So this is the my message on behalf of university to all the participant. Kindly convey this message to your colleagues. Don't do such kind of practice, because this is for your knowledge only. We are trying to enrich your knowledge. Okay, we are doing hard work like Dr. Khajaji and ICT PMC committee, project monitoring committee, along with the ICT Colonel Venkatji also watching. Okay, that how many participants are very much serious. So no issue, you may quit and you need not to attend at all. Okay, if you are not interested, but don't do such kind of practice, and especially in this ICT program. Okay, so this is my personal advice and suggestions, that if you are really serious, then attend continuous sessions, because we are taking the services of such a renowned professor like Dr. Nikhil from IIT Bhilai and NIT and foreign universities, only for the pure benefits. Okay, thank you.
Thank you, Kare sir. And
So next session will start at 12 p.m. So you
yes,
may
sir.
around 7 minutes.
Next session will be
Refreshment.
of the session 4 from Dr. Prashant V. Varidar from MNIT Bhopal. I advise all the participants that kindly make a note that the session will be started within 10 minutes. Thank you all. Sir, good afternoon, sir.
Good afternoon. Good afternoon, sir.
Sir, just now we have ended with the first session of the day 2.
Okay.
The participants have already been informed that the next session will be from yours, and it will be starting by 12 noon today.
Okay.
So within 5 minutes, we can start your session, sir.
No problem.
Yes, sir. Thank you for joining on time, sir.
My pleasure.
speak up.
Good afternoon, one and all present here.
Mhm.
Welcome to day 2, session 4 of this week-long faculty development program. I take this privilege to now invite Dr. Prashant V. Baredar as our subject expert to give a short briefing about his illustrated professional career. I would like to share that Dr. Prashant V. Baredar is currently the chairman of Department of Energy
ये
Center.
रविशंकर जी, आप अपना वीडियो ऑन कर लीजिएगा। अपना वीडियो आप ऑन कर लीजिए। जो प्रेजेंटर रहे कम से कम वीडियो से दिखता रहेगा तो अपीयरेंस ठीक रहता है।
जी सर, अभी video is not working, sir. I have been trying for a while, sir. It was waiting.
बोलिए आप बोलिए।
Yeah.
ठीक।
He has a PhD in thermal engineering. He has successfully led 8 projects which involves sensitivity analysis and optimization of hybrid system of solar, wind and biomass, and evaluated downdraft gasifier in RGPV campus using different biomass BRECs for electricity generation for Madhya Pradesh Council of Science and Technology, and also successfully has led 2 projects for Ministry of New and Renewable Energy. He has been awarded various awards for his extreme good work. He has carried out electricity generation projects entirely based on captivating wind power of capacity 250 kilowatt under RESCO. We are very honored to have him on board. He has led various projects, and I'm sure with his expertise in all such varied fields, this session is going to be very interesting and very fruitful. I have the privilege to invite Dr. Prashant Baredar, sir. Sir, please.
Thank you very much, sir, for such a nice introduction.
Thank you very much, sir.
At the outset, I would like to extend sincere thanks to the organizing committee of this FDP Faculty Development Program for allowing me to share my views with you. And I welcome all of you in this session. A very good morning, you all. I am Dr. Prashant Baredar, Professor.
Good morning, sir. Good morning.
Good morning. Professor and Head, Energy Department, Maulana Azad National Institute of Technology, Bhopal. And topic of my today's presentation is heat transfer analysis and kinetic modeling of anaerobic biodigestion. So let me share my presentation. Facing some problem.
For any technical issue, sir?
No. Is it visible to all of you?
Yes, sir.
Okay.
Full screen.
So basically this presentation is based on waste utilization. Now all of you know what is waste. Any discarded material which is no more useful for us, that is waste. And if that waste is organic waste, that is more problematic, because organic waste, if you keep for certain period of time, it start degrading, deteriorating, decomposing, and as a result of that, a lot of problem arises. So the idea is that if such a waste is utilized in a better way, to have some useful product. So that's what my topic is. That is on waste utilization. Waste utilization. So different routes are there for utilizing this waste. We'll discuss it one by one. But before starting the actual presentation, I'm just giving you a little bit idea about what the topic is: heat transfer analysis and kinetic modeling of anaerobic biodigestion. So any organic waste that can be decomposed mainly in two ways, either aerobically or anaerobically. You must be knowing about that. If that waste is decomposing in the presence of air, that is aerobic decomposition. But if the waste, if you keep that waste in a closed container, and if you are not allowing any exposed to the air, still it will decompose, and that will be an anaerobic decomposition. Both have some merits and demerits. In the anaerobic decomposition, as you are not exposing it to the external environment, there it will decompose, and the bacteria or microorganisms which are responsible for the decomposition process, they are the anaerobic bacteria. And if you are not keeping any care, just in the open air, open atmosphere, if you are allowing it to decompose it, that will be aerobic, and the bacteria or microorganisms which are responsible for that, they are of aerobic nature. If you compare this aerobic and anaerobic, you will find a lot of advantages and disadvantages of both. In the aerobic, the major disadvantage is that as this decomposition process takes place in the open air, lot of mosquitoes, flies, insects breeds over there, and they spoil entire atmosphere. Whereas anaerobically, as you are keeping that waste in a closed container, there are no chances of breeding of these mosquitoes, flies, insects and all. The entire atmosphere will remain hygienic.
So, PPT, could you please go with the full screen, sir?
It is full screen.
But here we are not getting the updates, sir.
Just a minute. Now it is full screen.
No, sir, no, sir. Once again, you share the screen as a whole window, sir.
Okay, okay. Now it is full screen.
Yes, sir.
Okay. So we are talking about the aerobic and anaerobic digestion. So a little bit care is needed for making it anaerobic digestion. And the major advantage of anaerobic biodigestion is that useful gas, that is methane gas, can be produced with the help of anaerobic biodigestion, and that methane gas
Sir,
is called, yes,
sorry to disturb, sir, but PPT is not visible, sir.
PPT is visible.
No, sir.
What's the problem? Now is it visible?
Yeah, sir. Go for just a full screen, sir.
Yeah, yeah. Now it is not full screen, but is it visible?
Yeah, it is visible.
Now I am making it full screen. I have made it full screen. Is it full screen now?
No, sir.
What's the problem? Is it not at all visible, or is it is not full
Sir,
screen?
may I suggest something?
Yes,
You
yes, please.
just press F5, then it will
Yeah, yeah,
become
yeah.
up
I
to.
have pressed F5. I have pressed F5 and made it full screen.
Sir, have you?
Okay,
I know
I
that.
think
I know that.
it is.
Share the screen as a window, sir.
Yes, yes, yes. You need to share your screen then, so that whole
So once
screen
you
will be visible.
once
Even
you
though
click
it is. I mean,
once
we
you
can
click on
see it,
stop
but
presenting, sir. Once you click on stop presenting and just share the screen and click on the complete window screen.
Okay. Now I shared the screen.
Now you go with the sir full screen.
Yeah, that's what I'm doing. F5. Now I have made it full screen.
So could you mail the PPT? Shall I go with my
Okay, okay,
side?
okay, okay.
I think we could manage the view also. It is not that it is not visible at all. We can, I mean, it is my suggestion if the participant agree, so that the session could be taken forward. But thing is, actually, the slides are not moving also. I don't know.
Just I'm receiving the file from the keynote and I'll be presenting from my side. The
Yeah,
slides.
that will be very fine.
Okay, I have
That
made
will be
you.
very
Okay, I have made you.
Thank you.
I have made you.
Yes, sir.
You got my mail?
Yes, sir. Received.
Okay.
I hope
So-
it is visible, sir. Full
Yeah,
screen.
yeah, it's visible. So the idea about this presentation we were talking about the anaerobic biodigestion. So if any waste, if you are keeping in the open air, there are a lot of problems can arise with that. Okay, so there will be aerobic decomposition. Whereas if you keep such waste in a closed container, there also decomposition process will take place, but that will be anaerobically. And actually, this in this anaerobic biodigestion process, the useful gas can be prepared, that is methane gas, and that methane gas can be used as a very good fuel. Now, for the formation of this methane gas or biogas, the very three essential three things are there. That is the atmosphere which is needed. That is wet, warm, and dark. Wet, warm, and dark. Okay, that means just go back. That means the anaerobic decomposition process which takes place. For that process, adequate temperature should be there. That is why I have carried out heat transfer analysis. That is my first part of the presentation. And second part of the presentation is kinetic modeling. Now, what is this kinetic modeling? Just go back. What is this kinetic modeling? So, in the kinetic modeling, kinetic means the movement of the bacteria or microorganisms which are responsible for the this process, that is decomposition process. Actually, the quantity of this microorganism, that is in crores of quantity. That is in crores. Okay. So they grow and multiplies in the slurry. Okay. And their growth or multiplication rate, that matters actually. That is why the kinetic modeling is needed, means number of growing bacteria, number of dying bacteria, what is the growth rate. So model is prepared for that. Okay, so that all comes under kinetic modeling. So actually there are two parts of my presentation: heat transfer analysis and kinetic modeling. Next, please. Now the question arises in our mind that this bioenergy or any bio waste, whether it is renewable source of energy or not. So that can be understood by this carbon cycle. So here in the carbon cycle, you can see any organic matter or bio waste that is in the form of any plants, woody biomass. Okay, so that can be eaten. That is eaten by animals and human beings, and the carbon dioxide which is exhaled by animals and human beings, that can be again taken by the plants for making their foods with the help of photosynthesis process. All of you know the photosynthesis process, because in the photosynthesis process, with the help of carbon dioxide and the water in the presence of sunlight, plants there prepares their food. Okay, and that plants or foods is again eaten by the human beings and animal. Okay, and these plants releases carbon dioxide in the atmosphere. Then other source is that this woody biomass can be used as a fuel in the industries or for cooking needs. Again, the carbon dioxide is released in the form of smoke. That carbon dioxide is again taken by the plants in the photosynthesis process. So you can understand from this carbon cycle that this cycle is repeated again and again. Okay, that is why we can say that this bioenergy or bio waste is a renewable source of energy. It can be renewed again and again. Next, please. As I told you earlier, there are various routes or various processes for utilizing bio-waste or organic waste. They could be classified as a thermochemical conversion, biological conversion, or physical conversion. In the thermochemical conversion, a combustion is there, pyrolysis is there, gasification is there. Combustion, as you all know, combustion is actually open burning. If you burn any woody biomass in the open atmosphere, combustion takes place. As a result of that, heat is produced. Then the second route is pyrolysis. In the pyrolysis, if you burn this woody biomass in the presence of limited amount of air means previously limited amount of air, then you have to stop further supply of air. Okay, so pyrolysis will take place. So the first process is actually a carbonization. Okay, carbonization, then liquefaction, pyrolysis, then the gasification. Okay, so that is actually a gasification process. And in the gasification process, the intermediate steps are the carbonization process and liquefaction process. Carbonization and liquefaction process. Okay, liquefaction is that process is actually a pyrolysis process. So what happens actually in this process? Whatever woody biomass is there, that you have to keep in the closed container, and initially little bit amount of air is supplied. That is for just for initiate the burning, and after that the amount of supply of air is completely stopped. Okay, so there enriched amount of carbon is produced. That is actually a carbonization process. Generally takes place up to 250 to 300 degrees Celsius. Okay, then the second stage is the liquefaction process, where that solid carbon enriched product is converted into the liquid based sticky star based compound. Okay, that is a liquefaction process, and then that liquid based compound is converted. That process takes place at around 500 to 550 or 600 degrees Celsius. And then if you further increase the amount of heat, that liquid or sticky tar based compound is converted into gaseous form. That is a gasification process that takes place at around 1050 or 1100 degrees Celsius. Okay, and as a result of gasification process, the gas which is produced, that is producer gas. Okay, that producer gas is also very good cooking fuel, can be used as a cooking fuel. Okay, so one more process is there which is a little bit different from the combustion process, that is incineration process. So incineration is in between the gasification and the combustion. Okay, in the incineration process, a large amount of heat is supplied. Actually, in the incineration process, the waste which can be used, that can be organic as well as inorganic waste, and large quantity of heat is supplied like a combustion process. Okay, and the container in which this process takes place, that is called incinerator. Okay, and as a result of that incineration process, a large quantity of heat can be produced. So generally you will find in the large size hospitals, incinerators are there, because in the hospitals you will find large amount of inorganic waste is collected every day, and they have a problem of storing such waste, because you know that in the hospitals the atmosphere inside the atmosphere inside the hospital, that should be hygienic. Okay, but every day you will find that caps of the bottle, then empty bottles, caps, then syringes, plastic waste, different types of inorganic waste is collected every day. So it's not possible for them to collect and store such waste, because otherwise it will unnecessarily occupy the lot of space. Unnecessarily a lot of space will be occupied then keeping such waste in a storeroom, okay, that will spoil the entire atmosphere. It will not remain hygienic for a longer period, okay. So they have to get rid of such waste. So if they have the incinerator in their premises, they can put such waste, inorganic waste, in the incinerator, and in the incinerator it can be combusted, and as a result of that, large quantity of heat can be produced, and that heat they themselves can use, because you know in the hospitals they have to wash cloths, curtains, bed sheets, hanky every day. They have to sterilize different items. So large quantity of steam is needed. So by using this heat, steam can be produced, and that steam can be used for sterilization purposes, different OT equipment, operation theater equipments, then for washing different cloths, curtains, etc., bed sheets. Okay, so they have dual advantage of this incinerator. One side they are getting rid of such inorganic waste, and other side they are converting this inorganic useless waste in the useful energy, okay, which they themselves can be utilized. Okay, so that is a incineration process. So all these are the thermochemical conversion routes. Okay, then in the biological conversion, fermentation and anaerobic digestion is there. Okay, and fermentation means what? Fermentation is life without oxygen. Life without oxygen. So they have also various applications in the bakery, then dairy items or bakery items, or wines, or any alcohols or any medicines can be prepared with the help of fermentation process. There are various type of fermentation process, that is acidic fermentation, alcoholic fermentation, and useful products can be produced with the help of this fermentation process. Okay, dairy item, bakery items like breads, then in the dairy item like curds, then different cakes, etc. Okay. Now the other application is anaerobic digestion. So my presentation is mainly based on the anaerobic decomposition process. Here in this anaerobic decomposition, as I told you that the decomposition process takes place anaerobically. That means in the closed container, which is called digester. Okay. Here you have to put all the organic waste inside the digester, and some period is required for decomposing it completely. That period is called retention period. Okay, and actually that retention period varies from type of waste to waste. Okay, so actually some of the waste can be decomposed easily, so it requires less retention period, whereas some of the waste that requires more period for decomposition process. So they require more retention period. Okay. As a result of that, we can get a useful gas, that is methane gas, which can be used for obtaining heat. And second thing is that after completely decomposing it, and you can collect the useful gas, that is methane gas, and the leftover slurry which will remain there. Okay, that can also be used as a very good manure or fertilizer. Okay, manure. Okay, and you will surprised to know that the manure which is obtained with the help of this anaerobic decomposition process, that is more nutritious than the composting one. Because composting means what? Composting is open air aerobic decomposition. Composting is open air aerobic decomposition. Whereas in the anaerobic decomposition also, you will get leftover slurry, and that leftover slurry can be used as a very good manure, okay, and that will have more nutritious value as compared to the composting one. Because you will find here that in the aerobic decomposition process takes place in the open atmosphere, and most of the nutritious contents they get escape out. Whereas in the anaerobic decomposition process, this process takes place in the open atmosphere, in the closed container, and here the whole things get conserved, and 100% you can say that 100% utilization is there, because as the decomposition process takes place, most of the part is converted into gas, that is methane gas, that can be collected in the gas collection chamber, which can be used as a very good fuel for fulfilling cooking needs and for heating application. And the remaining part which will left there, okay, that also will not be wasted, that also can be used as a very good manure, okay. And main thing is that will have more nutritious value, okay. Then the other route of this waste utilization is physical conversion, that is squeezing, okay. If any the seeds which contains oil, okay, so from that means some edible oil and non-edible oils are there. So at least non-edible things from there, that vegetable oil can be extracted, okay, and that can be converted into the biodiesel, okay, with the help of transesterification process and other processes, okay. So that is also one of the route for converting that waste into useful item. Next, please. Next, please. So that's what I told you, that aerobic decomposition we have already discussed, that aerobic decomposition takes place in the presence of oxygen, and as a result of aerobic decomposition process, carbon dioxide, ammonia and some other gases are prepared, okay. But you will find that this ammonia, that is very toxic, okay, and along with carbon dioxide, okay, so they contribute to the greenhouse gases, okay. And this aerobic decomposition process, that is a uncontrolled reaction. You cannot control that reaction, because as this process takes place in the open air, okay, will not have your control over it, okay. Most of the contents will get escape out, because as that process takes place in the open air, and human beings and animals are wandering here and there, so most of the waste content that will get escape out, okay. So there will be huge quantitative loss as well as qualitative loss in the aerobic decomposition process. Whereas in the anaerobic decomposition process, you will find that as the complete waste you are putting inside the reactor, okay, so there are no chances of quantitative loss as well as qualitative loss, okay. And the heat which will be produced in the aerobic decomposition process, that you will not be succeed to capture it, okay. And definitely final product will be in the form of fertilizer that you can use as a composting fertilizer, but that will not have that much nutritious value, because most of the nutrients will already get escape out. Next, please. So as compared to that, anaerobic decomposition is more useful than the aerobic one, because here there is no any quantitative as well as qualitative loss. Everything will be conserved, because most of the waste which you are keeping in the closed container, there it will get decomposed and will be converted into useful gas. That gas can be collected in the gas collection chamber, which can be used for fulfilling your cooking needs or obtaining heat, okay. In the anaerobic decomposition process, the gases which are generally produced, they are methane gas, carbon dioxide and some hydrogen and other traces of gases, but they are in very little quantity, okay. Major constituents are methane and the carbon dioxide. So methane, percentage of methane is around 60-65%, whereas 30-35% carbon dioxide is there. But if you want to use this methane gas or biogas as a fuel, okay, it should not contain carbon dioxide, because you know that carbon dioxide is fire extinguishing gas. Fire extinguishing gas. So you need to separate this carbon dioxide from this methane gas or biogas. Okay, so for that purpose, some purification processes are there. That means that methane gas or biogas you can pass through the alkaline solution, where it, that carbon dioxide will get absorbed and form calcium. If that alkali is calcium carbonate, then calcium bicarbonate will produce sodium carbonate. Sodium carbonate or potassium carbonate will produce by absorbing this calcium carbon dioxide. Okay, and remaining gas will be CO2 free. Remaining gas will be CO2 free. So in this process, in this way, you can purify this methane gas or biogas. Okay, by removing this carbon dioxide, and remaining gas will be CO2 free. Okay, then you can use it for obtaining heat. Okay, and that will have more heating value, calorific value. Okay. Next, please. As far as composition of methane gas is there, methane is having a share of around 50 to 70%, whereas carbon dioxide, that is second and largest compound, that is 30 to 40%. Then hydrogen 5 to 10%. Nitrogen is 1 to 2%, and moisture content, that is water vapor, that is very less, that is 0 to 1-3%. So, and H2S, that is hydrogen sulfide, so that is very less, traces amounts are there. Okay, so major combination is of methane and carbon dioxide. So for using this methane gas or biogas for obtaining heat, okay, you need to remove carbon dioxide, because CO2 is a fire extinguished gas. Okay, next please. Now this, how this anaerobic digestion process takes place. So this anaerobic digestion process takes place in 3 different steps. So first step is the hydrolysis step. Second is the acetogenesis stage, acid forming stage, and third is the methogenesis stage or methane forming stage. Okay. So the first step is, that is hydrolysis stage. In the hydrolysis stage, hydro means water. So in the hydrolysis stage, what happens? Whatever the organic waste is there, equal amount of water to be added, making it in the form of slurry. Okay. So where this organic waste get completely dissolved in the hydrolysis stage. Okay. But if this organic waste contains, if it contains complex or waste organic, that is carbohydrate, protein, lipid, then that will be converted into simple soluble organics. Polymer based compounds are converted into simple monomer based compound. So that's what all happens in the hydrolysis stage. So here most of the complex compounds get solubilized in the water. So this is actually hydrolysis, or sometimes also called liquefaction stage. Okay, where all these complex compounds get solubilized. Okay, and the period of this hydrolysis stage is around 3 to 4 days. Okay, after that this slurry or waste is transferred into second stage, that is acid forming stage or acetogenesis stage, where propionic or butyric or acetic acid is produced. Okay, pH value is slightly decreased up to 5.5. Okay. So that is why this stage is called acetogenesis stage. Okay. Then, and the period of this acetogenesis stage is around 4 to 5 days. Sometime it is 6 to 8 days also. Okay. After that, this acetic acid or propionic acid is transferred to the third state, that is methogenesis stage. Okay, in this methogenesis stage, this acetic acid is converted into methane based compound. Okay, in this way, methane gas is produced. But along with this methane gas, carbon dioxide is also there. Methane gas, carbon dioxide is also there. Okay. Then you may ask the question that how the carbon dioxide. So actually, whatever the waste is there, that is in the form of carbohydrates. Okay. And as the temperature inside the reactor or digester is very much high. Okay. So some sort of burning or combustion takes place. As a result of that, this CO2 gas is produced. Okay. And from this waste in the form of carbohydrates or protein, okay, methane gas is also produced. Okay. So in this way, methane gas or biogas is produced. Next, please. As far as hydrolysis stage is concerned, that is what liquefaction or solubilization process where the all the complex organic matters get solubilized in the water, or polymer based compounds are converted into monomer based compound. Protein based compounds are converted into polypeptide or amino acid. Fats are converted into glycerin, and fatty acid and amylose is converted into monosaccharide and polysaccharide. Okay. And the bacteria which decompose it, okay, they decompose the long chain of complex carbohydrate, protein and lipid into shorter parts and monomer based compounds. Next, please. The various bacteria which are responsible for this decomposition process, you can see here. This is microscope. This is a view you can see under electron microscope. So there are two types of bacteria actually, spherical bacteria and long tubular bacteria. Spherical shaped bacteria are called Methanosarcina genus, and long tubular bacteria are called Methanothrix bacteria. They appear like this under electron microscope. Next, please. Now, there are various operational parameters which are responsible for the performance of this anaerobic decomposition process. So we will discuss it one by one. So first is the operating temperature. As I told you earlier that temperature or warm condition is very essential for anaerobic decomposition process. Okay. Generally, three range of temperatures are there. That is psychrophilic, mesophilic and thermophilic. Below 20 degrees Celsius temperature range is considered as a psychrophilic temperature range. 20 to 35-40 degrees Celsius temperature range is considered as a mesophilic temperature range, and beyond 40-45 degrees Celsius is considered as a thermophilic temperature range. As far as base suitable temperature range is there, the mesophilic temperature range is best suited for this anaerobic decomposition process. Okay, because below 20 degrees Celsius that decomposition process will not take place, and beyond 40-45 degrees Celsius temperature is there, then in that case definitely decomposition will be there, but instead of methane content there will be more quantity of carbon dioxide, because instead of decomposition there will be a combustion. Okay, so more quantity of carbon dioxide will be there, and if more quantity of carbon dioxide is there, then in that case calorific value or heating value of this fuel will be decreased. So then in that case you need to maintain your mesophilic temperature range inside the reactor or digester. Okay, but if the temperature falls below 20 degrees Celsius, then in that case your decomposition process will not start. Okay, that is why heat transfer analysis is carried out. Okay, we will see it in the next subsequent slides. Okay, so now the second environmental parameter which affect, that is the retention time. Okay, retention time means what? As I told you earlier, that the period which is responsible for completely decomposing the waste, that is called retention period. Okay, and if the waste, organic waste, is more complex, then the retention time will be more. Okay, for example, stem roots are there. Okay, stem roots, they are more complex. Okay, so that will take more time to decompose, whereas dry leaves or kitchen waste, okay, which can be easily decomposed, they will take less retention time. Okay, then organic loading rate. So first we have to see what is this organic loading rate. Organic loading rate is actually a frequency of dumping that waste in the reactor or digester. Okay, so that should be optimum frequency of dumping that waste in the digester. Okay, because that frequency is, if that frequency is more, then in that case that waste will get accumulated, and the proper mixing or stirring of this waste will not happen. So most of the bacteria will remain occupied in the particular area, and they will not mobilize from one place. They will not move from one place to other. Okay, so that will actually affect the rate of decomposition process. Okay, and very slow loading rate. If very slow loading rate is there, then in that case also the quantity of gas which will produce, that will also less. Okay, as far as pH value is concerned. Okay, generally in the acetogenesis stage, that pH value is around 5.5 to 6.5. Okay, whereas in the methogenesis stage, that pH value rises up to 7.5. Okay, or more than that. Okay, then whatever the bacteria or microorganisms are there, they are very pH sensitive bacteria. Okay, so you need to monitor pH value in the different stages of the decomposition process. Okay, then the next parameter is the seeding. Seeding means what? Seeding means actually the word seed. Seed, you know. Okay, seed, from seed a plant germinates. Okay, so here this term seeding is taken, that is to initiate the reaction. Okay, to initiate the reaction. Most of you must be knowing that how that curd is prepared. How that curd is prepared? Curd is prepared by using adding little bit amount of previously prepared curd in the milk. Okay, so same thing happens here. Previously quantity of previously digested slurry, little bit amount of digested slurry is added in the fresh slurry. Okay, so that is actually a seeding process. So by seeding process, you can reduce your retention period. Okay, and the seeding actually accelerate the rate of reaction. Seeding actually accelerate the rate of reaction. Okay, then the toxic substances. Okay, whichever waste you are using, that should be purely organic. It should not inorganic waste, because these organic anaerobic bacteria are very sensitive bacteria. Okay, so they should not be, there should not be inorganic waste, as well as the water which you are using for pouring in the reactor, that should not contain any toxic waste like heavy metals like nickel, chromium. Generally what happens for such a reactor or biodigester, the industrial wastewater is used. Okay, but you have to take proper care that that industrial wastewater, that should not contain toxic heavy metals like nickel, chromium, zinc, nickel, chromium. So that care you need to take. Then the CN ratio. CN ratio means what? CN ratio is carbon to nitrogen ratio. Okay, carbon to nitrogen ratio. So the desirable CN ratio, carbon to nitrogen ratio for anaerobic decomposition process is 30:1, means 30 part of carbon to the 1 part of nitrogen is needed. Okay, actually carbon is needed for supplying the energy. Carbon supplies the energy. Okay, whereas nitrogen is needed for building the cell structure. Nitrogen is needed for building the cell structure. That is why both these carbon and nitrogens are required for this anaerobic decomposition process. Okay, and if there is somehow scarcity of this or shortage of carbon percentage or nitrogen, okay, then in that case you need to add some carbon contents or nitrogen contents. So for carbon contents, more carbohydrates can be added. For nitrogen contents, if there is shortage of nitrogen, then in that case more amount of leguminous plants or seeds can be added to take care of shortage of nitrogen. Okay, apart from the CN, that is carbon and nitrogen, one more thing is needed, that is phosphorus. Okay, phosphorus is needed for accelerating the rate of reaction. For accelerating the rate of reaction. So the very rich source of phosphorus is night soil. Okay, that is human waste. Okay, so 1% of night soil or human waste, if you add, okay, that can be very good source of phosphorus. Okay, so it is actually needed for accelerating the rate of reaction. Okay, now the next parameter factor is moisture content. Okay, so adequate quantity of moisture is needed. Okay, because as you all know that as already I told you that most of organic decomposition process that is required means the three essential parameters which are required for organic decomposition process, they are wet, warm and dark. Means adequate quantity of moisture should be there, warm condition should be there and dark condition should be there. Okay, so moisture content is there, means in the anaerobic reactor around 75 to 80% moisture content should be there. 75 to 80% moisture content should be there. Okay, if not, more quantity of water should be added. Okay, because at your home also you might have seen that if any dried thing is there, that will not decompose easily. For example, newspaper. If newspapers are there, and newspapers are actually organic waste, and if you keep this organic newspaper at any almirahs, okay, they will not decompose. Okay, but if you dip that newspaper in the water and then you keep in the almirah or any container, okay, after a certain period of time, it will smell badly. It will smell badly. What does it indicate? It indicates that decomposition process has been started. Okay, so moisture content is needed. Okay, at your kitchen also, in your kitchen also, you will see the things which are moisture content, in which moisture content is there, they will get spoiled easily. They will get spoiled, whereas the dry things that will not get spoil easily. Okay, so moisture is also needed for anaerobic decomposition process. Then as far as process operating parameters are there, first thing is the type of digester. Okay, so various types of reactors are there, like batch type digester, continuous type digester. So according to your utility, means if at your home you want to install the reactor or digester, okay, it would be better to install continuous type digester, because the waste which you are generating, that is every day you are generating the waste, and for fulfilling your cooking needs, okay, you need every day the cooking gas, okay, that is methane gas. Okay, so it would be better to have continuous type digester, because continuous type in the continuous type digester, every day you are putting the waste and every day you are getting the useful gas. Whereas in the batch type digester, once in a week or once in a 15 days or once in a once in a month, one batch of the waste you are putting, okay, for certain period of time. So that is batch top digester. So for community uses, generally for community uses where the waste is get collected not that much frequently, that is once in a week or once or twice in a week or thrice in a week or twice in a 15 days. Okay, so their batch type digesters would be better. Okay, then type of feedstock. Okay, so kitchen waste, then garden waste or any type of organic waste which you are using. Okay, so which type of feedstock you are using, that also affects the performance of anaerobic digester. Okay, because that if that feedstock is easily digesting, it is easily decomposing, so then in that case less retention period will be required. But if a complex waste is there, okay, complex woody biomass is there, then in that case more retention period will be needed for complete decomposition process. Okay, so that also affects the performance. Then digester configuration. Okay, the size of digester, what should be the dome shape, then volume of the digester. Okay, so that actually depends upon the quantity of waste you are having every day, okay, or in a batch. Okay, so accordingly you can design the digester, and how much from that digester, from that waste, generally what happens, from 1 kg of waste around 0.3 to 0.34 cubic meter methane gas can be produced. Okay, so accordingly the size of the dome that you can choose. Then mixing is very essential for the proper functioning of this reactor, because proper stirring is needed for the properly homogenizing of this mixture. Otherwise, what will happen if proper or frequent stirring is not there? Then in that case, most of the bacteria will be accumulated at one places, and they will not move from one place to another. So that will affect actually the growth rate of the bacteria or dying rate of the bacteria. Okay, so proper mixing is needed for proper functioning of the anaerobic decomposition process. Then feeding frequency. We have already discussed that the number of times you are feeding, that actually depends upon whether you are using the batch type or continuous type. In the continuous type, every day you are putting that waste in the digester, whereas in the batch type, once in a week, once in a 15 days, in a batch you are putting that waste. Okay, so accordingly that feeding frequency is decided. So all these are the environmental and operational parameters of this anaerobic reactor. Okay, next please. Impact of temperature we have already discussed, but still I will tell you that this sacrophilic temperature range that ranges from 15 to 25 degrees Celsius, whereas mesophilic temperature range 35 to 40 degrees Celsius, thermophilic 45 to 60 degrees Celsius, but base temperature range is 35 to 50 degrees Celsius. Okay, and if somehow there heat loss is there, okay, so you need to maintain that much temperature inside the reactor. That is why this heat transfer analysis has been carried out. Next please. So for carrying out this heat transfer analysis, one trial has been taken in our energy center. So for that, the substrate which we have chosen, that is Parthenium hysteroporus, okay, and the kitchen waste. So sort of co-digestion we have carried out. Okay, Parthenium hysteroporus is a widely available weeds in our campus. Okay, so generally after rainy seasons, huge quantity of Parthenium hysteroporus is there. Okay, and that is actually means presence of this Parthenium hysteroporus is very unhygienic. Okay, and only way to get rid of this Parthenium hysteroporus is to burn it. Okay, so instead of that, we have decided to use this Parthenium hysteroporus as a substrate for carrying out the anaerobic biodigestion process. Okay, so and to increase reduce the retention period and or for making the rate of reaction faster, along with the Parthenium hysteroporus, we have used kitchen waste also, because in the kitchen waste the rotten things are there. Okay, which get easily decompose. Okay, that is why co-digestion we have done. Okay, next please. So this is the bioreactor we have used for carrying out the, yes, just a minute.
Excuse me, sir.
Yes, please.
Sir, can we use any type of salt for substrate, like black salt?
Yeah, you can use that. Additives can also be used. Okay.
Yes.
Which will enhance the production. Okay.
Yes, sir.
So this bioreactor we have used, that is of size 1 cubic meter. Okay, 1 cubic meter methane gas can be produced in this bioreactor. Next please. So we have carried out this proximate analysis of this Parthenium hysteroporus, whose moisture content was around 80.26 and ash content on the dry basis was 3.31. Volatile matter on the dry basis was 12.63 and that of fixed carbon was 3.80. Next please. Generally any organic waste or woody biomass or any organic waste has three major constituents, that is lignin, cellulose and hemicellulose. Okay. So as far as Parthenium hysteroporus is there, in that Parthenium hysteroporus, that is lignin that is bonding compound, that is 13.9%, whereas cellulose, their percentage was 27.8%, and hemicellulose is 21.01%. Next, please. So we have monitored the temperature inside the reactor because as I told you that the mesophilic temperature range is best suited for the reaction to take place. Okay, so it was essential to monitor the temperature every day. Okay, so outside and inside temperature per day. Okay, this was the average temperature we have monitored. Okay, and how much heat losses were there, that we have carried out. Next, please. So for carrying out the heat transfer analysis, the slurry temperature we have measured, that was 37 degrees Celsius, and that time actually we have taken this trial in the month of November. Okay, so that time ambient temperature, air temperature was 15 degrees Celsius. The dome which we have used, the thickness of metal dome was 0.005 meter, whose thermal conductivity is 62.403 watt per meter Kelvin. Okay, and with the help of thermocouples, we have used the temperature inside the air within the dome. So it was 35 degrees Celsius. So thus heat transfer analysis we have carried out, that is from slurry to the air within the dome and from the dome to the atmosphere. Okay, so generally there were three ways of the heat transfer. Okay, three modes of the heat transfer, that they were radiative, convective, and evaporative. Okay, so next, please. So we have calculated this radiative, convective, and evaporative heat losses using these expressions. Okay, so the radiative heat losses, okay, that is actually given by Dunkel. Okay, so this expression we have used. Okay, so emissivity, then Stefan Boltzmann, sigma is the Stefan Boltzmann constant. So their value is 5.67 into 10 to minus 8. Okay, TW is the temperature of slurry, and T is the air inside the dome. Tg is the temperature of the air or temperature of the gas inside the dome. Okay, so by putting this value, we got the radiative heat by radiation. The heat transfer which took place, that was 5.35 watt per meter square Kelvin. Then by convective route, we use this expression given by the Fernandez and Chorga in 1990. Okay, by putting this value, but before that we have calculated the pressure of the slurry as well as pressure of the air inside the dome, that is Pg and Pw. Okay, with the help of this expression, that is which is given by the Fernandez and Chorga. Okay, so with respect to that temperature, and by putting this value of pressure and temperature, we got the convective heat loss coefficient, that was 1.33 watt per meter square Kelvin. Next, please. Then the evaporative heat transfer heat loss coefficient was carried out with the help of Cooper equation, that is which is given by Cooper in 1973. Okay, so here we have used this. There actually 1.33 is actually convective heat loss coefficient. Convective heat loss coefficient. Okay, so by putting the value of convective heat loss coefficient in the evaporative heat transfer coefficient, we got the heat loss by evaporation, that is 12.55 watt per meter square Kelvin. Okay, so thus the total heat transfer coefficient from the slurry to the enclosed air, that is actually the summation of this radiative, convective, and evaporative. So that was that comes out to this 19.23 watt per meter square Kelvin. Next, please. So this was the heat loss between the slurry to the air inside the dome. Now we have calculated the heat loss from the top of the dome to the ambient. Top of the dome to the ambient. So for this, the expression given by the Duffy and Bachmann in the 1991, that was used. That is SC is equal to 5.7 into 3.8 V, where V is the velocity of the air blowing. Okay, so that time the velocity of air blowing was 3.1. Average velocity of blowing was 3.1 meter per second. So SC, which is used for that value, velocity of air, we have calculated. So it was 17.1 watt per meter square Kelvin. Okay. So by considering all these values, we have obtained the overall heat transfer coefficient, that is from top of the dome to the ambient air, Okay. So that heat loss coefficient, here you can see the expression for the overall heat transfer coefficient, that is 1 upon Hi plus L upon K plus L upon K HO. Okay. So 1 upon 19.2 was the heat transfer coefficient from the slurry to the air inside the dome. Okay. 0.005 is the thickness of the dome. K is the thermal conductivity. Okay. And 17.1 is the heat transfer coefficient from the dome to the ambient. Okay. So that heat transfer coefficient was 9.04 watt per meter square Kelvin. That means that much heat losses are there. Okay. So you need to take that heat losses. You need to consider that heat losses. So by adopting some external means, okay, you have to take care is that heat losses. Otherwise, your rate of decomposition that will reduce drastically. Okay. So by using some reflectors or by supplying some hot air, hot water or hot air through the slurry. So there are some external means by which you can raise the temperature inside the slurry. Okay. So this is the heat transfer analysis. Okay. Next, please. Next, please. So that is actually a first part of my presentation. Now the second part of presentation is a kinetic modeling. So for the kinetic modeling, I have used the model presented by scientist Monod. Okay, so Monod model is there. Okay, so that I have used for monitoring the bacterial growth. Because growth of bacteria, growth rate and rate of growing, rate of dying, and rate of multiplication, that is actually very essential for the this rate of decomposition process. Okay, because the quantity of this bacteria present inside the reactor, that is in crore or millions of bacteria are there. Okay, so growth rate or maturity rate or dying rate, that matters actually. Okay, so this bacterial growth is a complex process involving numerous anabolic and catabolic reactions. Okay, so ultimately this biosynthetic reaction results in cell division. Okay, so bacteria multiplies by the cell division process. Okay, so the medium supplies all nutrients required for growth, and environmental parameters are optimal. The increase in number of bacteria and their bacterial mass, that can be measured as a function of time to obtain the growth curve. Next, please. So the life cycle of this growth bacteria, that can be studied in 4 different phases, that is lag phase, exponential or log phase, stationary phase, and death phase. Okay, so this growth curve constitute 4 phases: lag phase, exponential phase, stationary phase, and death phase. Okay, so generally initially the bacteria which are there in the embryonic stage, okay, that is actually a lag phase. Okay, then they start growing and growing in the size, okay, and multiplying. So that is actually exponential phase. Okay, then one stage is reaches where that there actually the rate of growing and rate of dying, that is almost equal. That is actually a stationary phase. Just a minute, I will answer at the end of the session. Okay, so that is stationary phase, where the rate of growing and rate of dying bacteria is almost equal. Okay, and the last phase is the death phase. So in the death phase, there is more rate of dying bacteria as compared to rate of growing or rate of multiplying bacteria. Okay. Next, please. So this is actually a bacterial growth curve. Okay, you can see here in the graph. Okay, so initially first is the lag phase, so then the exponential phase, then stationary phase. Okay, so in the stationary phase, both the rates, that is growing and dying rate, is almost equal. In the death rate, dying rate is increased, okay, as compared to the growing rate. Okay, so in the different phases, respective that anabolic and catabolic reaction takes place. Okay, next please. So this is the very first stage of this bacterial growth curve, that is the lag phase. So that is very first phase. So here growth rate is essentially 0. Okay, because here just means embryonic stage bacteria are there. Okay, newborn bacteria are there. Embryonic stage bacteria are there. Okay, that is why growth rate is almost 0. Okay, and after placing inoculum into fresh medium, that is in the form of seeding. Okay, growth begins after a period of time. That is actually a lag phase. Okay, and that lasts from minutes to several hours. Okay, that depends upon means how, whether you have used seeding phenomena or not, or whether that means the waste which you have used, that is easily decomposable waste or not. Okay, etc. Next please. Then the length of lag phase depends upon the type of medium as well as initial inoculum size. Okay, so initial inoculum size means actually newborn bacteria, their sizes, okay, quantities, that matters actually, and accordingly the length of lag phase depends. For example, if an inoculum is taken from an exponential phase, means for seeding purposes, if the inoculum is taken from the exponential phase and is placed into the fresh medium of 10⁶ cells per ml, okay, under the same growth condition, that is temperature, shaking speed, there will be no noticeable lag phase. Next please. So this is the second phase of bacterial growth curve. So here the growth and rate of increase of cell, that is maximum compared to the other phases. Here the largest growth rate occurs, okay, and rate of increase of cell, that is also more as compared to any other phase. Okay, and the number of cells increases in a geometric progression, that is 2:0, 2:1, 2:2, 2:3, 2:n, like 2:n. Okay, you can understand it from the next slide. Next please. Here you can see single cell is there, then after the cell division, okay, there will be that cell will be divided into 2 cells, then further each cell will be redivided into 2 more cells. Okay, so in this way cell division takes place. Okay, 2:0, then 2:1, 2:2. So in the geometric progression this cell division occurs. Okay, and in the exponential growth phase, okay, these bacteria grow and multiply, okay, with the help of cell division. Next please. So in the monod model, this cell growth during the exponential phase, because this is very remarkable phase of this bacterial growth curve, exponential phase. That is why in the exponential phase, the cell growth can be described using the expression dx by dt is equal to mu x, where x is the number or mass of the cell. X you can consider number of bacteria, or x you can consider as a mass of cell also, because mass is also growing. Number of bacteria is also growing. Okay, number of bacteria is also growing. Okay, so x, that is considered as a mass per unit or number of unit per unit volume, number per unit volume. Okay, and t is the time. Okay, mu is the specific growth rate constant, that is per unit time. Mu is the specific growth rate constant, that is per unit constant. Okay, so this exponential phase has been expressed in terms of dx by dt is equal to mu x. Next, please. Then the stationary phase, here you will observe no net growth rate is there. So that is why we can express this dx by dt is equal to almost 0. Okay, and although there is no net growth in the stationary phase, that doesn't mean that there is no cell growth is there or division is not there. Definitely cells still grow there, and also cell division will take place, but that will not remarkable. Okay, little bit amount of growth rate and division will be there. Okay, and that growth is balanced by equal number of cells dying. That growth will be balanced by equal number of cells dying. That is why this is called stationary phase. Okay, here growth rate is equal to dying rate is there. Growth rate is equal to dying rate is there. Okay, so almost equal is there both the rate. That is why this phase is called stationary phase. Next, please. Next, please. Last phase is the death phase. Okay, that is the final phase. So here there is a net loss of culturable cell. Okay, and rate of dying the bacteria, that is more. Okay, rate of dying the bacteria, that is more. So growth and cell division is there, but loss of cell is more. Okay, so that means in the if you say that in the death phase will there be a growth or cell division? Yeah, definitely growth or cell division will be there. Okay, in the death phase there is no, as such, there is no any watertight compartment among this lag phase or exponential phase or stationary phase or death phase. Okay, in all the phases all the activities occurs, but remarkable thing is that in the death phase more dying rate is there. That is whereas the cell division or growth rate is negligible, very negligible. Okay, even in the exponential phase loss of cells are there. Okay, so all the activities takes place in all the phases, but in that particular phase particular rate is remarkable, whereas rest of the rates are negligible. Next, please. Next, please. So here is, go back, please. So Jacques Monod, he is the scientist. In the 1940s, he has developed one model known as Monod model. Okay, where he presented one equation, Monod equation, which studies the bacterial growth rate and the substrate concentration. Substrate concentration means whatever the slurry concentration is there. Okay, which is responsible for growth rate. Okay, so what is the effect of that substrate concentration? This is very essential. Okay, so here you can see mu is equal to mu max S upon Ks plus S. Okay, this is the equation presented by Jacques Monod in 1940. Okay, where mu is the specific growth rate per unit time, mu max is the maximum specific growth rate per unit time for the culture, S is the substrate concentration, that is mass of the bacteria per unit volume, and Ks is the saturation constant, that is mass per unit volume, that is also known as affinity constant. Okay, so also it is called as a half saturation constant, means at the half saturation there is a half of the mass, there is a saturation. Next, please. Next, please. So this equation was developed. Go back, please. This equation was, next, please. Next, please. So this equation was developed. Go back. So this equation was developed from a series of experiment trial which were taken by the Monod, and after taking series of trial, he developed that equation. Okay, and result of this experiment showed that at low substrate concentration, growth rate becomes a function of substrate concentration. So this was the finding of this Monod model. Okay, so the Monod designed equation to describe the relationship between the specific growth rate and the substrate he considered two limiting next please. He considered two limiting cases in this monod equation, so which he express here. Okay, so dx by dt is equal to mu max Sx upon Ks plus S. In this equation, monod has given two limiting cases. The first case is higher substrate concentration. Higher substrate concentration as compared to the saturation constant. Okay, so where S is very much high as compared to the saturation constant. Okay, so then in that case, when S, that is substrate constant, when substrate concentration is very high as compared to the saturation constant. Okay, so that means the saturation constant is very negligible. So then in that case, you can neglect this Ks. Okay, so then in that case, this equation 2 will become mu max Sx upon S, then Ss will get cancelled, and this equation will become dx by dt is equal to mu, dx by dt is equal to mu x. Okay, mu max x. Okay, so this is the first limiting condition. Next, please. Next, please. The second limiting case occurs at the low first we have to consider high substrate concentration. Second limiting case is low substrate concentration. So when the substrate concentration is very low as compared to the saturation constant, then in that case this equation 2 will become is dx by dt is equal to mu max Ss upon Ks. Okay, there we have ignore the effect of the substrate concentration which is in the denominator, and this equation 2 will become equation 4. Okay, so as shown in the equation 4, when the substrate concentration is low, growth rate, that is dx by dt, is dependent on the substrate concentration. Since the substrate concentration is in the numerator, as the substrate concentration decreases, the rate of growth is found at the end of growth curve as the substrate, and that which will nearly consume the completely. Next, please. Then they have correlated this specific growth rate with the cell yield. Okay, so in this monod equation, it can be expressed in terms of cell yield also. So growth is related to the substrate utilization by a constant called cell yield. Okay, so that cell yield is expressed with the help of dx by dt is equal to 1 upon y dx by dt. 1 upon y dx by dt. So here you can put the value of dx by dt, that is growth rate. Okay, that is monod equation. Okay, so here y is actually the cell yield, that is mass per unit mass. Mass per unit mass means that is the mass of the bacteria per unit mass of the substrate. Mass per unit mass of the substrate. Okay, so the cell yield coefficient is defined as the unit amount of this cell mass produced per unit amount of substrate consumed. Next, please. So if you put the value of dx by dt, that is growth rate, in this equation number 5. So this equation number 5 will become ds by dt, that is cell yield is equal to minus 1 upon y mu max Sx upon Ks plus S. Okay. So as shown in equation 6, equation 2 and 5 can be combined to express this microbial growth in terms of substrate disappearance. Next, please. Now number of bacteria which are present, that can be counted in this way. Okay, so how they can be counted? See here. Okay, so a glass plate is taken, and over the glass plate the sample is added, and over the sample this cover slip is put. Okay, the gap between the cover slip and the glass plate, that is 0.02 mm, that is 1 by 50 mm. Okay, and this cover slip it's plotted with the help of horizontal and vertical line forming a grid, thus having a 25 large square, which is having a total area of 1 mm square and a total volume of 0.002 mm cube. Okay, so under electron microscope, if you observe this sample, okay, so microscopic observation, all cells are counted in the large square. So in each square, how many cells are there? they can be easily counted. Okay, so 12 cells, 12 such cells are there. Okay, so in how many several squares are there? So, and in each square, how many cells are there? So they can be multiplied. So to calculate number per millimeter of sample, 12 cells multiplied by 25 large scale. There were 25 large cell in the whole grid we have seen, and in each cell we have seen 12 cells are there. So 12 multiplied by 25. Okay, the gap between the cover slip and the glass plate, that was 50. So 15 to 10 raised to minus 3. Okay, 15 to 10 raised to 3. Okay, so in this way we can calculate per ml or per cubic centimeter how many bacteria are there. Per cubic centimeter or per ml how many bacteria are there. So by adopting this process you can count the total number of bacteria. Next please, per ml. Next please. So how the kinetic modeling is carried out, that you can see here, the cell growth during the exponential phase is given by dx by dt is equal to mu x. Okay, so where x is the number or mass of the cell, both can be considered, either number of bacteria or mass of the bacteria. Okay, mu is the specific growth rate, t is the time. Okay, so if you integrate it, dx upon x is equal to mu dt. Okay, if you integrate it, okay, so this expression you can see here. Okay, after integration by putting a limit x0 to x, and from time 0 to t time up to, and x0 means initial number of bacteria to the final number of bacteria. Initial number of bacteria to the final number of bacteria. Next please. Okay, so after integrating it, log x is equal to mu t plus log x0. So it can be then x is equal to x0 into e raised to power mu t. Okay, then for going on multiplying or cell division when occurs, x upon x0, that initial bacteria and final bacteria. Okay, so twice means a double for doubling. Okay, x to be double, x upon x0 is equal to 2. So 2 is equal to e raised to mu t. Okay, and as far as stationary phase is concerned, then in that case dx by dt is equal to 0. Next please. So in this monod equation, that is mu is equal to mu max s upon ks plus s. We are already seeing mu max s, ks, ks is actually affinity constant or saturation constant. Okay, so you can rearrange this equation, mu is equal to mu m into mu m, that is mu max, into s upon ks plus s. Okay, next please. Now taking reciprocal mu 1 upon mu, then numerator will come to the denominator and the denominator will go to the numerator. Okay, so by taking reciprocal of this equation number 7 will be there, which is actually a Lineweaver-Buck equation. Okay, so this equation is 1 upon mu is equal to ks plus s upon mu m s. Okay, so it can be rearranged again. So ks upon mu m into 1 upon s plus 1 upon mu m, ss will get cancelled out. Okay, so 1 upon mu m. Okay, so this is in the form of equation of straight line. Y is equal to mx plus h. Y is equal to mx plus h. Okay, so y means 1 upon mu, y intercept, m that is slope, that is ks upon mu m is slope, x means 1 upon s. Okay, plus h. Okay, next please. Just go back. The next. So you can see ks upon mu m is a slope. Okay, 1 upon mu m is a y intercept. Okay, and minus 1 upon ks is a x intercept. Okay, so you can plot this graph against 1 upon mu upon 1 upon s. S is a substrate concentration, whereas mu is the growth rate. Okay, mu is the growth rate. Okay, so how they behave with respect this substrate concentration with respect to growth rate, that can be obtained by plotting this graph with the help of this monod model. Next please. So in this way, we can obtain the nature of how this substrate concentration, how this growth rate behaves with respect to substrate concentration with the help of this kinetic modeling by using this Monod model. Okay, so in this presentation, we have carried out this heat transfer analysis and kinetic modeling. What was the purpose of heat transfer analysis? What was the purpose of heat transfer analysis was to find out the heat losses in the anaerobic digestion. Accordingly, if there are heat losses, then that much heat losses can be covered with the help of some external means. Okay, because as I told you that if the temperature drops down, then in that case your rate of decomposition that will also decreases. Okay, so there should be a proper temperature inside the reactor. Okay, so you need to take care of heat losses. Okay, there should not be adequate heat losses. Okay, so for that purpose we have carried out heat transfer analysis. Okay, and second was the kinetic modeling. Kinetic modeling means the movement of bacteria and their specific growth rate of the bacteria growing and multiplying, and the dying rate of the bacteria. Okay, and according to the concentration of the waste, substrate concentration, how they behave, how they varies, growing rate, dying rate, and growth rate. Okay, that you need to study. Okay, for proper functioning of this anaerobic decomposition process. Okay, that is why we have carried out this kinetic modeling. Okay, so with the help of this graph, which we can plot with the help of Monod model, okay, you can obtain the relation between this specific growth rate and the substrate concentration, and how they behave with respect to each other, that can be studied. Next, please. So these are the conclusions. Okay, how many heat losses were there, and the relation between the substrate concentration and the specific growth rate. Next, please. Next, please. Next, please. So these are some of the references. Okay. Thank you. And if you have any queries, please feel free to ask me now.
The participants are requested, if at all you are having any queries, kindly do ask.
Hello.
Hello.
Sir, I have a question.
Yes, please.
Sir, which bacteria will be optimum for a biogas plant producing high value of gas?
Actually, two bacteria are there, Methanosarcina and Methanogenous. They have very good results. They have very good result for anaerobic decomposition process.
Methyla, sir, once again, please.
Methanosarcina and Methanogenous.
Methanogenous. And sir, what we can do in the for storage of this produced gas? Actually, balloons are required, but that is also not for longer use.
Actually, the gas which is produced inside this reactor or digester. Okay, you can collect it in the gas collection chamber, or any balloons can also be used. Balloons can also be used for storage purposes. Okay, or even sometimes your tire tubes.
The amount of methane is reduced after storing for long.
No. Actually, generally the gas which is produced, okay, it contains along with methane, carbon dioxide and H2S, hydrogen sulfide is also there. Okay, so that you need to remove before using that, because actually whatever the gas you are producing, that you are going to use for as a fuel or for obtaining heat energy. Okay, but you know that carbon dioxide, that is fire extinguishing. Okay, so that will not support the combustion. So you need to remove that carbon dioxide. Okay, so you can pass this gas through alkaline solution where it get absorbed. Okay, and forms carbonates. Okay, and remaining gas will be CO2 free.
Okay, sir.
So any more participants may raise question like Biswajit ji? Biswajit is doing very well. Actually, I expect that all participants must interact. It should not be the delivery from one side. It should be the dialogue delivery from both sides. Okay, so participant like speaker Prashant ji has narrated very important aspects of on the topic of this anaerobic biodigestions. So you should interact and take the advantage of the speaker. Professor Dr. Prashant ji, I am very much thankful for your nice presentation. May I ask one question, that what are the limitations of this kind of models, this kinematic modeling of anaerobic biodigestion?
Yes, sir. Limitations actually, definitely we can say it's an approximate model. The accuracy of this model depends upon the accurate monitoring and measuring of these bacteria and these substrate concentration. And in the organic waste, we have seen there are various type of waste and various composition. So accordingly, that substrate concentration you need to monitor properly, and the accuracy depends on all this.
Okay.
Sir, actually, I'm from electronics background.
Yes.
And you have very beautifully elaborated the process of getting this biomass digestion.
Mr. Amit Kumar,
Yes,
whenever
sir.
you are asking any participant, whenever asking anything else, then you may please open the video. Okay.
Yes, sir.
It will be more, you can say, beautification of the
Actually,
interaction.
my camera is not working on my laptop, so
Okay,
I'm sorry
okay.
for that. Even though the camera is on, but I don't know, it is not coming.
No issue,
from
no
last-
issue. Please,
last
no issue,
week.
no issue.
Yes,
Please
sir.
speak.
Yes, sir. Yes, sir. So I am from electronics background. I was asking you, is there any alternate method for the electronic waste digestions also? Means it contains very harmful materials. The electronic waste contain very harmful material. So I wish to know if is there any other way, means similar way for the such waste digestion, the electronic waste digestion.
Definitely, but this is exclusively for the organic waste. But if electronic waste is there, then in that case, the incineration process in the incinerator for obtaining heat energy, it can be useful if that electronic waste contains inorganic waste. But if some more useful or precious metals are there, so that you need to separate before that. Okay, then any inorganic waste that can be combusted in the incinerators, and by incineration process, heat energy can be obtained, and that heat energy can be utilized for different causes.
Okay, sir. Thank you, sir. Thank you. Very informative session, sir. Thank you for that. I also thank the organizers also. Thank you, sir.
Thank you, Amit sir, for clearing the query. Any more participants? The query regarding the session.
Dr. Prashant ji, we have many friends in your MI and IT.
Sir.
Dr. D. Kishan ji, I am from Civil Engineering Department.
Yeah.
D. Kishan Kant from NIT in Civil Geotechnical Engineering. He is my friend.
Kishan Dharawat.
And I am the principal of this University Engineering College.
Sir.
And our Honorable Vice Chancellor is also passed out from MA NIT Bhopal. Earlier it was MST Bhopal.
Achha.
Yes, sir.
Nice to meet you, sir.
Very nice to see you, sir. Very nice session, and more questions within 2-3 minutes, so that we can give you some break, and after 2 p.m.
Even after this session also, anytime if anybody have any queries or doubts or difficulties, they can contact me, they can approach me. My contact details are with organizer of this FDP. Okay,
Yes,
so
yes.
they can get that, and anytime they can contact me.
Correct.
Participants are most welcome for any further queries.
Actually, during this undivided state, Madhya Pradesh and Chhattisgarh, this
Yeah.
Bhopal is the very renowned regional engineering college.
Yes, sir.
Yes. So thank you, sir. And Dr. Khaja ji, please conclude the session.
Yes, sir. Yes. So I'm very thankful for our session for keynote speaker, Dr. Prashant sir. Sir, very thank you for your sparing your valuable time from your busy schedule that too on Sunday. Thank you so much, sir. You have given the session on kinetic modeling of anaerobic biodigestion. The speaker has discussed about carbon cycle and the way through which we can use the chemical and biological waste to generate the energy. He has very well explained about the anaerobic decomposition and as well as digestion. This session included calculations of heat transfer coefficient from the slurry to the enclosed air. He has also discussed very effectively about the bacterial growth curve as well as Monod model as well as its Monod design equation. Overall, he has been explained about the kinetic model for the anaerobic biodigestion method. So finally, my sincere thanks to Dr. Prashant Baredar from MNIT Bhopal. Sir, I am very thankful to you, sir, for sparing once again your valuable time. As well as for your kind information, sir, the FDP is for the 6 days completely. We have been segregated into 5 different themes: energy, environment, sustainable development, education policy, as well as case study. So with these words, I once again thank Dr. Arun Khare sir for providing the platform of conducting this FDP on behalf of CSVTU AICT program. On behalf of BIT Raipur, I thank all the participants for connecting this session. And for a kind information, after 15 minutes, the next session 5 will be from Dr. Francisco Liberty. He will be connecting us at 2 p.m. Thank you, one and all.
Thank you, Khare sir, and Khwaja
Thank you, sir.
for
Thank you.
allowing
Thank
me
you,
to
sir.
share my views.
sir.
And
Thank
thank
you,
you
sir.
for patience hearing. Thank you, sir.
प्रशांत जी, कैसा है वहाँ भोपाल का माहौल अभी? क्या है, कोविड में अभी शांत हुआ कि नहीं हुआ?
अभी तो काफी कंट्रोल में है सर. डेली 11 से 12 केसेस निकल रही है.
एमएससीटी में भी प्रॉब्लम थी?
एमएससीटी में हाँ, एमएससीटी में भी प्रॉब्लम था. दो फैकल्टी और
अच्छा
4 नॉन टीचिंग
अरे बहुत
एक्सपायर्ड हो गए. तो
यहाँ
प्रॉब्लम
पर
तो
भी
पूरे
सर-
सिटी में ही था.
छत्तीसगढ़ में भी एक्चुअली बहुत प्रॉब्लम थी.
हाँ,
ये तो डॉक्टर सविता व्यास है, राजीव गांधी यूनिवर्सिटी से, आरजीपीवी से.
जी जी जी.
मैंने पीएचडी वहीं से की, आरजीपीवी भोपाल से, सिविल इंजीनियरिंग में.
अच्छा अच्छा अच्छा.
डॉक्टर सविता व्यास और यहाँ पर सीएसबीटी टेक्निकल यूनिवर्सिटी में मैं, ये हम दोनों मिलकर ये ज्वाइंटली ये प्रोग्राम करा रहे हैं, एफडीपी प्रोग्राम.
हाँ हाँ.
बहुत सारे 23,000 क्वेश्चन बैंक को ट्रांसलेट करना है, आईसीटी के सारे यानी कोऑर्डिनेट वहां से सविता व्यास कर रही हैं.
अच्छा अच्छा.
छत्तीसगढ़ स्टेट से मैं कोऑर्डिनेट कर रहा हूँ.
अच्छा.
तो काफी बड़ा प्रोग्राम हो रहा है. एक्चुअली 3 साल तक लगातार ये सेशन चल रहा है. इस फाइनेंशियल ईयर में 3rd सेशन है और इस तरह से चलते रहेंगे लगातार.
नहीं
इसमें क्या है सर, ज्वाइंटली एग्रीमेंट है इन टेक्निकल यूनिवर्सिटी भिलाई के साथ में एआईसीटी का, तो 50-50% शेयरिंग है.
अच्छा अच्छा.
जो अभी तो जो ऑनलाइन प्रोग्राम हो रहा है उसमें तो पूरा 100% एआईसीटी दे रही है. ऑनलाइन प्रोग्राम में क्या है, 3 लाख का रहता है 1 वीक प्रोग्राम. 1.5 लाख रुपए यूनिवर्सिटी को देना है और 1.5 लाख रुपए AICTE को फंडिंग करना है।
अच्छा अच्छा।
रिसोर्स पर्सन के लिए AICTE दे रही है पेमेंट,
हम्म।
लॉजिंग बोर्डिंग के लिए जो है वो यूनिवर्सिटी प्रोवाइड कर रही है।
लॉजिंग बोर्डिंग तो होगा ही नहीं, सब ऑनलाइन ही होगा।
अभी तो ऑनलाइन है, लेकिन लॉजिंग बोर्डिंग जैसे अभी हम लोग नॉन टीचिंग प्रोग्राम करवा रहे हैं 5 जून से, तो वो टोटल ऑफलाइन प्रोग्राम है, उसको मैंडेटरी कर दिया कि ऑफलाइन ही होगा वो।
अच्छा
अभी
अच्छा।
छत्तीसगढ़ में कंट्रोल है, तो ऑफलाइन में होगा तो वो 12 दिन का है, तो लॉजिंग बोर्डिंग यूनिवर्सिटी करेगी।
हाँ हाँ
तो बाकी अभी तो ये ऑनलाइन है, तो उसमें दिक्कत नहीं है, इसमें तो कोई प्रॉब्लम ऐसी नहीं है। तो नॉन टीचिंग का प्रोग्राम टोटल ऑफलाइन ही हो रहा है।
अच्छा अच्छा, चलिए बढ़िया है।
तो बढ़िया, चलिए सर, आपके संपर्क में रहेंगे सर।
बिल्कुल बिल्कुल सर।
डॉक्टर YK शर्मा आपके जो डायरेक्टर थे MACT भोपाल के,
हाँ 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 हाँ।
वो मेरे हेड ऑफ द डिपार्टमेंट थे सिविल इंजीनियरिंग में, जबलपुर GEC से हूँ।
अच्छा अच्छा अच्छा। हाँ हाँ।
जबलपुर इंजीनियरिंग कॉलेज से मैंने BE किया था सिविल इंजीनियरिंग में।
अच्छा अच्छा।
वो मेरे HOD थे डॉक्टर YK शर्मा साहब, आपके डायरेक्टर।
हाँ हाँ, हमारे डायरेक्टर थे हाँ।
हाँ ऐसा ऐसा।
काफी काफी साल वो बंसल इंजीनियरिंग कॉलेज में भी डायरेक्टर
हाँ
रहे।
बंसल इंजीनियरिंग कॉलेज में थे, वो तो राष्ट्रपति के भांजे हैं ना, सगे।
हाँ हाँ हाँ।
संजय शर्मा थे उनके सगे भांजे।
हम्म।
तो चलिए सर, आपका बहुत बहुत धन्यवाद सर।
चलिए
और
बहुत
आप
बढ़िया
आए,
सर, बहुत अच्छा लगा।
Thank you.
चलिए
थैंक यू सर,
Thank you once again, Prashant sir.
थैंक यू
थैंक यू
सर,
सर, थैंक यू।
थैंक यू।
एंड खरे सर, हमारे नेक्स्ट कीनोट डॉक्टर फ्रांसिस्को लिबर्टी आ चुके हैं सर, ज्वाइन कर चुके हैं। हेलो सर,
Good morning.
डॉक्टर
Hello, good
फ्रांसिस्को
morning.
लिबर्टी।
Good afternoon. Good afternoon. Can you hear me?
सर, योर वॉइस इज वेरी लेस, वेरी लो।
Okay, I will try to do something. Is a bit better now?
Yeah, now it's better, sir.
Okay, thanks.
So, very good
I'll try to-
afternoon for sparing your valuable time.
Good afternoon, and thank you very much for inviting. It's really a pleasure to be here. It's really, I'm honored. So, I will start the presentation, okay? I will share my screen.
Just now the previous session has been completed, sir. So as per our schedule, it is at 2 p.m., sir.
Okay, so we need to wait a bit. Okay,
Yeah,
sure.
just for 12 minutes, sir.
Yes.
Okay, I will take this time to polish further the presentation and double check it. Okay.
Surely, sir. Surely, sir. It's a pleasure.
Thanks.
Okay.
Thank you, sir. Thank you.
We're looking forward to hear you, sir.
Thank you very much.
Thank you.
Welcome. Good afternoon, Dr. Professor Francisco Liberty.
Good afternoon. Good afternoon.
Good afternoon.
Thank you.
So, how many times you have presented in India?
Sorry?
How many times you have presented the webinar in Indian universities?
No, this is actually the first time. So it's,
this is the first
really,
time. Okay.
It's really a pleasure.
So really, it's also a pleasure for us that today you are with us. So I welcome you, sir. And now requested to organizer, Dr. Khaja Saab. Please introduce about Professor Francisco Liberty, who is researcher and project manager at Sapienza University of Rome, Italy.
Yes, sir.
Okay.
Benvenuto, sir.
Yes, please.
Benvenuto Liberty, sir.
Okay.
We are honored to introduce Dr. Francisco Liberty as our next speaker. To give a brief introduction about our speaker, Dr. Francisco Liberty is a research fellow in automatic control at the Sapienza University of Rome. He is currently working mainly on cyber physical systems and smart grid control problems, using mainly optional control and machine learning techniques. He teaches system and control methods to cyber physical security, and indeed it sounds very interesting for all of us to hear more about this, sir. He has a PhD in system engineering from Sapienza University. A few years back, Dr. Liberty served as Energy Research Project Manager in INEA, that is the Innovation and Networks Executive Agency, European Commission, Brussels. He has carried out applied research in several European funded projects and taking up project management roles as a team leader, work packet leader, task leader, and has got 60 publications in his name. We are honored to have you as our speaker, sir. We are eager to hear you. The stage is yours. Welcome, sir.
Thank you very much for the kind introduction. It's really a pleasure to be with you all today. So I'm really honored. I'm going to share some of the current and past research activities that I did together with my colleagues at the University of Rome La Sapienza.
Sorry to interrupt you, sir. Could you please speak a bit louder?
Okay.
Yeah, now it's better, sir. Now it's better.
Okay.
Yeah, thank you very much.
Thank you very much. So, thank you for the invitation. It's really a pleasure to be here. And today I'm going to share some of the current and past research activities that I am doing together with my colleagues at the University of Rome La Sapienza. They are focused a lot on energy sector. I will keep the level of the presentation quite high, but I will give all the details to the publications for any deepening of the study of the subject. And of course, I remain fully available to provide additional explanations today or later. It will be a pleasure, of course, to keep contacts. So I'm going to share the screen with my presentation. And I hope now you see the screen. I will try to maximize Partner. Okay, can you see the screen?
Yes,
screen
yes,
right?
Sir.
Okay, thank you very much.
Visible.
Thank you. So good afternoon again. My name is Francesco Liberati. I work at the University
Your
of Rome La
voice is again
Sapienza.
going feeble, sir.
Sorry?
Your voice is again going feeble.
Sorry, I cannot understand.
Yeah, now it's clear, sir. Your voice was going low again.
Okay. Sorry for this. Maybe I will close the camera because at the end we don't need it. So I will save some bandwidth. Okay. Okay, so hopefully now you hear me clear.
Yes, sir.
Thank you very much. So currently I work at the University of Roma Sapienza at the Department of Computer Control and Management Engineering. So there we specialize in informatics and in automatic control. We have a long tradition, especially in automatic control of linear and nonlinear systems. I work at the Network Control Laboratory. So it's a laboratory which is headed by Professor Francesco Deli Briscoli, and there we specialize in control problems applied to networks. So it is telecommunication networks, transport networks, and myself, I focus mostly on energy networks and cyber-physical systems, and in particular on the cyber-physical security of the power system of the smart grid. So the title of this presentation is Optimal Control of Distributed Green Energy Resources in Weakly Connected Microgrids. We've done many works in the sector. Today I'm going to focus on mostly two topics. So I'm going to talk about smart charging of electric vehicles to start, and then I'm going to discuss about energy management in a smart household, in a building. But the same methodologies that I'm going to present here can be applied also in general for the control of microgrids. So they are portions, usually small portions of the grid that are connected or not to the main power system. So the connection can be either present or absent. And there is a lot of interest around the scenario in which we have a microgrid that is weakly connected to the power system, meaning that this can mean many things. So for example, that the power that the microgrid can take from the grid is low compared to the power needs that the user have in the microgrid, or we have an intermittent situation in which we have power only some hours of the day, or similar, let's say similar ideas.
So it's still in the first slide itself.
Yes. Sorry.
Okay.
Now I'm going to switch. Thank you.
Yes. Thank you.
And I have about 1 hour, if I remember well. Is it okay?
Yeah, we are having exactly 90 minutes, sir.
Okay, perfect. Even better. Thank you very much. Okay, so I'm going to present an introduction, and then, as I said, the focus on these two use cases. So fast charging control in a service area, and then I'm going to focus on smart home control, and then some conclusions. The level of the presentation, as I said, it will be high level. I will introduce some formulas and I will explain them, but the very detailed formulation, it's presented in the papers. So this is the reference scenario for the presentation of today. So it's the power system. So as we know, it's divided into a power generation, let's say, sector on the top. Then we have the power and transmission sector, characterized by very high voltage level and very long distances of the lines, of the electricity lines. Today I'm going to focus more on the distribution side, which is at the bottom. So it's the sector that is closer to the consumption, closer to the end users, and it's characterized by medium to low voltage levels, as we know, and medium to low power flows. In particular, the topic, this presentation will focus on some keywords, which are storage control, renewable energy sources, okay, and microgrids, so decentralized systems. So in particular, I'm going to present some reference scenarios in which we control very specific portions of the grid, not the entire grid as in traditional optimal power flow control problems, but rather specific sectors of the grid which are of interest. So as we know, this is relevant because in many countries the grid is ongoing a rapid transformation with the introduction, especially of power generation, distributed power generation at medium and low voltage levels. So it's like wind, solar, and tidal energy, which is depending on a primary source that is not programmable. And so, of course, this, as you know, introduces difficulties in the planning and in the operation of the grid. For this reason, we need to introduce, let's say, control and intelligent functions at lower level of the grid, closer to the customers. This is also very relevant in, of course, developing countries or in countries where we don't have a strong transmission system. Okay, so it's very important to have intelligence and control functions at the lower level, at the distribution, medium and distribution level. So a keyword is distributed generation, of course, also given the push that we have towards reaching, as we say in Europe, a climate neutral economy. So the goal, it's in really few years, 2050, to reach in Europe a climate neutral economy, which means that power needs, first of all, should be reduced. So it's a topic of energy saving. And then after we have done a dramatic, let's say, energy reduction and energy saving push, or while, let's say, the effort is to get the energy that we need only from sustainable and renewable sources. In this way, we can have a climate neutral economy, which means that the economic growth does not anymore, let's say, comes at the expense of the environment. So distributed generation, of course, is a goal. Nowadays, it's also possible, as you know, given the even that dramatic decreases in the prices. Then the other keyword is energy storage, and we know that we need a lot of energy storage in the grid, namely because we have non-programmable generation, and so it's becoming even more difficult to match generation with the demand. Okay, which is one of the primary requirements in the grid, to keep always the balance between what we generate with the power plants and what the users consume. So energy storage under many different forms. There are a lot of different technologies. Now, today I'm going to focus on batteries, so lithium-ion batteries, for example, and I'm going to talk about fixed storage, so residential storage, for example, in houses or in microgrids. And I'm going to talk about electric vehicles, which is another form of storage, as you wish, if you wish. Then we have microgrids, basically, at the bottom. So this is the reference scenario. I'm going to focus on the lower part of the picture. So the first problem is the first presentation. The first part of the presentation will be focused on fast charging control in a service area. I'm going to present two different scenarios in which we control electric vehicles that are recharging. Now, the topic of electric vehicles charging, it's very important for all the reasons that I explained before. It's going a radical shift from petrol-based, combustion-based engines to other technologies. Of course, is ongoing, and this is relevant because the transportation sector, at least in Europe, is responsible for a very large percentage of the CO2 emissions. Okay, so if we want to reduce that, we need to change the status quo in the transportation sector. A path that now it's getting momentum, at least in Europe, is that of electric vehicles, of course. And this poses again significant challenges to the smart grid, because basically, if we have a large shift from combustion-based engines to electric vehicles based engines to electric vehicles, sorry, then we have further stress on the grid. First of all, in terms of the demand, there will be logically a big increase in the demand because the energy will no longer come from gas or petrol, but from the electric system. Then the second point is also an impact in terms of the fact that many thousands or millions of vehicles will need to be recharged every day. And as we will see, these are systems that have very high power density and very high power demand in terms of peak power. So we have basically two options. Either we reinforce the grid, which means investing really billions and billions of euros to strengthen the grid, or we embed in the grid some intelligence, so some automatic control functions that are able to manage these charging peaks, okay, that we have when we have vehicles connected to the grid and starting the recharging process. So I'm going to focus on electric vehicles charging. Two slightly different scenarios, as I said. The first one is fast charging or ultra fast charging control in a service area. So as we will see, you can imagine the scenario in which we have like the gas stations, the normal gas stations that we have nowadays, at least in Europe, we have this new concept of service area, electric service area, that is basically a gas station where you can plug in your vehicle and recharge it very fast. Okay, and I think, for example, that one of the first service areas of this kind was installed exactly in Italy, in Rome, by Enel. So I'm going to discuss two different approaches, control approaches that we have used. One is PMP, which stands for Pontryagin Maximum Principle. It's a mathematical optimization technique that we have used recently for addressing this kind of problem. Another technique, which is a very traditional one, I would say, it's MPC, which stands for Model Predictive Control. Now, of course, when you have different problems, we always have to look for the best methodology to address that problem. So far, we have seen that PMP, so continuous time optimization, is really suitable for this first scenario that I'm going to present, which is ultra fast charging in a service area, meaning that the user needs to have the electric car recharged in minutes, really in few minutes. So it's very, very high power levels. The second one, model predictive control, we have been applying it for many, many years, more than 10 years now, in energy control problems in which there is no such a stringent time requirement. Okay, so we have, for example, in this case, we have applied it for the case in which we have long recharging sessions. Imagine the case in which a worker arrives at the office with the electric vehicles, plugs the electric vehicles at the garage of the office, and then leaves the vehicle for the entire day there plugged. Okay. In that case, the vehicle can be used, for example, to provide ancillary services to the grid, but we don't have a very strong time requirement in terms of fast control computation, because the vehicle is plugged for many, many minutes or hours or days. Okay. So let's see the scenario for the first problem. So fast charging control. We are talking about a service area. Here on the top left, we see a small picture like a gas station where we have charging stations. So there we have only one car connected to one charging station, but of course you have to imagine that we will have many charging stations, some like tens of charging stations, few charging stations. So in this scenario, the driver arrives at the charging stations and really wants the car to be recharged as fast as possible, of course. So for this reason here, we have very high power levels in terms of charging power. So if I'm not wrong, the latest standards, they allow for charging at around 400 kilowatt, okay, which is really a huge amount of power. So for this reason, the charging session will last some seconds or minutes, and charging will be uncontrolled, meaning that the goal is to provide really the charging power that all the charging power that is requested by the driver, and ultimately, I mean, by the vehicle through the battery management system. So in this scenario, we want to recharge at maximum possible level, typically as fast as possible. Then this, of course, poses significant challenges, both in technical terms and also in terms of the business case, as I will tell you. From the technical side, of course, we have charging at hundreds of kilowatt, which is really a huge amount of power. And this needs to be planned both from the infrastructure side, of course. And here we have the need, as we will see, really to embed a control algorithm to manage this huge amount of charging power to avoid that the impact on the grid is negative. But maybe the most important motivation here is from the business side. This because at least in Europe and in Italy, when you have a microgrid, so let's look at the figure on the right, top right. Okay, so in the dashed box, you have what I call the service area. You can imagine it is the gas station, the traditional gas station equipped with electric charging stations. So we have some charging stations, the acronym is CS, and then it's a microgrid, okay, because we have a single point of connection, in this case, POC, point of connection with the main grid. Okay, and typically the point of connection, at the point of connection, we have a power transformer. Now, at least in Europe, in many countries in Europe and in Italy, the economic side of the problem depends on how large is the power flowing between the microgrid and the grid. So when we compute the tariffs, it's not only about how much energy we consume, okay, so kilowatt hours. So for example, how much energy we recharge into the vehicle, but it's mostly, I would say, about how we consume this energy. And in particular, if we have large power peaks at the point of connection, then this will increase the tariff that we have to pay. So the connection tariff depends on the power rating of the point of connection. So for example, standard connection tariff in Italy for residential sector is 3 kilowatt, 3.3 kilowatt. If, and of course, if the power consumption exceeds those 3.3 kilowatt, then the user is disconnected from the grid by a protection. Okay, and it's the same in an industrial or commercial setting as this one. So I was saying that power recharging happens at 400, for example, hundreds of kilowatts. So if we don't control this process, we end up with having huge power flows between the service area and the main grid. And these huge power flows of hundreds of kilowatts will make the cost prohibitive, basically, because of the connection fees. Okay, so with the connection fees, the higher is the power rating of at the point of connection, the higher you have to pay, basically. And we have done this work also in discussion with an Italian company very active in this sector, which is NLX, very active in electric vehicles control. And basically, if you do the analysis, you really see that you need to introduce a control action. Otherwise, the cost of the charging session for the end user is really too high and not competitive with the cost of recharging a normal vehicle, let's say. So for this reason, you see that we need to introduce, the idea is, which is very much explored, I mean, in literature, is to introduce a storage element. So this ESS, energy storage system. In our case, it's an electric energy storage system. And the idea is that we balance the charging power, which is indicated here with the letter, with the symbol W. We balance it with the storage. Okay, so discharging the storage, basically, we act in such a way that the charging stations will receive power from the grid, but also from the storage. And so, of course, the idea then is to recharge the storage, for example, at night or in the times of the day when we don't have a significant amount of charging sessions ongoing. So the whole idea is to lower the power flowing at the point of connection, okay? For example, from hundreds of kilowatts to few tens of kilowatts. And in this way, we will keep limited the connection fees, and we will make the this scenario feasible from the business point of view. So the goal really is to lower the power flow at the point of connection. Okay, so if we don't introduce any storage element, then basically you see that P will be equal to W, which means that if I have a charging session at 400 kilowatts, I will need to take 400 kilowatts from the grid. So I will have a huge power flow at the point of connection with the grid, basically. So what I'm going to present at a very high level, if you're interested, you can find it explained more in details in this publication that was just published on IEEE Control System Letters. This is one of the first works that we do with this methodology, and there is a lot of work to do still, as I will show. On the top right, we have, let's say, a illustratory sketch of the reference architecture. This can be implemented from the electrical point of view in several ways. Okay, I'm not expert in electronics and power systems and and power electronics, but this is an example of how this above scheme can be, let's say, implemented more in details. And here we show also the presence of the power converter. Because we are discussing still of an AC alternating current main grid, while instead, of course, the power is stored in DC, in direct current. So we need a conversion stage, DC-AC conversion stage. So this is, if you want, a bit an electrical translation of this high-level reference scenario on the top. So let's a bit dive into the mathematical formulation at a high level. Here we adopted a technique for continuous time control. Okay, it means that we have very high sampling rate, okay, of milliseconds basically, and so at every sampling time, we are able with this technique to compute in a very fast way the control action that we need. Something I did not say, but it's important to say, is that here the controlled system is the energy storage system. So I'm going to present a control algorithm which focuses on controlling the energy storage system. In practical terms, this means that at any time, so during the recharging process, but at any time of the day, we control the power flowing between the energy storage and the microgrid. Okay, so of course the storage can either discharge or recharge power, and so at any time we decide how much power the storage is discharging or charging, and the goal is to keep as low as possible the power P flowing between the grid, the microgrid and the grid. Okay. Now, this scenario is focused on smart charging, which is quite something that will be widespread in the future, okay, in future years. But really, the same scenario, you can translate it into already present situation or scenarios like smart buildings or a microgrid which has a weak connection to the main grid. Okay, really, similar formulation can be decided. here it's important to stress that, as I said, the charging process is uncontrolled. Okay, so it means that we need to provide all the power that the customers require. Okay, so this W is not a control variable, it's just a signal that we receive, and we need to provide that amount of power. Instead, U is a control variable, meaning that the algorithm will decide the optimal value of U, which is the charging or discharging power. So it's continuous time control, meaning that at any time, we, thanks to this control law, we can tell to the storage how much it needs to charge or discharge to ensure the optimal operation of the grid. It's based on a very popular technique, which is from calculus of variation and in general continuous time optimization, which is called Pontryagin maximum principle. As I said, the control variable is the storage power, so storage charging or discharging power. And if we want to summarize the control goals, they are these ones. So basically, to limit the power flow at the point of connection with the grid, to limit the displacements of the state of charge of the storage from a reference. This is an important point. I'm going to a bit stress this more. And finally, to satisfy the user preferences. So match the requested power.
Professor Liberty.
Yes.
Kindly speak loudly because your voice is very, very low.
Okay. Okay. I will try to.
So kindly keep your speaker near your. Yes, then it will be better.
Let me change the settings. Can you hear me better like this?
Yes, yes, and no issue if you can open your video, then I think there are no such kind of bandwidth issues.
Okay, let me see. I will try to open it again.
Yes,
so
now you yeah.
Okay, thank you. I think I had a problem with the microphone. Sorry for this. And I will try also to open the video.
Yes,
okay.
yes.
Perfect. Thank you very much. Okay, so the last point is to match the requested power from the users. It means that we need to provide all the power that is requested from the drivers, basically. Let me spend a few words on this second point. So here we are talking about the state of charge of the storage. So basically, how much energy we have in the storage. This is a crucial variable. Is a crucial variable really, because of course, if you have a storage that is full, for example, then you cannot charge it further. Okay. So for example, if you have a scenario in which you have a lot of renewable generation at that time of the day, but the storage is full, so you cannot store that renewable energy, and it will be either lost or it will go in the grid, which maybe is not the optimal thing to do. Vice versa, imagine the situation in which you have a storage that is empty, no energy in the storage. Then if you have a peak of charging requests, since the storage is empty, you cannot use it for balancing the charging power. Okay. For this reason, it is reasonable logic to have to keep the state of charge of the storage always close to a reference which is around 50% of the full capacity, because in this way you will have always some margin to either store energy, surplus energy, or provide balancing energy, so to either to charge or discharge the storage. So this is a technical goal that is not immediately, let's say, seen, but it's very important to include this in the problem formulation. Okay, so the on the right we have the from the paper we have the problem formulation. Mathematical problem formulation is an optimization problem in continuous time. So the idea is that we know the value of the charging power requested by the user on a given time window. Okay, So imagine the case in which you have either a booking system for the charging sessions, so you are able to plan a bit what is the expected power consumption in the next few hours, okay? Or even more simply, the case in which you have some cars connected currently, and so you are able to tell that to those cars, you need to provide a given amount of power until they will leave, basically. So in this second case, the time window over which we have a reasonable estimate of the charging power is shorter. It's some minutes or some minutes, I would say. But in any case, here we focus on a deterministic problem, meaning that we assume that we know the amount of power that the charging, that the electric vehicles will recharge, will ask to recharge, okay? For example, over a given day. So W is the aggregated charging power. Okay, so looking at the figure, W, it's this variable here, is the sum of the total power requested by the electric vehicles, going to the electric vehicles. And once again, we assume that, for example, thanks to a booking system, we know what will be this charging demand over the next few hours or minutes. Okay, so the problem basically is defined over a given time window that goes from the initial time, that is, for example, the current time, to a final time, okay, which is, for example, the end of the day. Then, this is a very simple formulation of the problem. So in this paper, we presented a very first and simple formulation of the problem. So let's focus first on the constraints, okay? So in optimal control, we need to define an objective function, that is this one, and then we need to define which are the constraints that we need to respect in the system. So this is an obvious constraint, of course. It's the balance. It's a balance constraint, which says that the power that is exchanged at the point of connection with the grid is the sum of the power exchanged by the storage plus the power exchanged with the electric vehicles, which is immediately seen from this picture here. Okay, so you see that P is equal to U plus W. So this is an obvious balance constraint. The second simple constraint is a dynamical constraint to model the storage. And this is the most simple model for a storage in continuous time that you can think of. And we use this exactly to keep the formulation very simple because we then are able to perform some other theoretical studies that we have in the paper, and I will discuss them. So we chose purposely to have a simple model of the system. So here U is the power charged if positive. Of course, if U is positive, it means that the storage is charging. If U is negative, it means that the storage is discharging, if we choose this convention, of course. So U is the charging or discharging power of the storage. X is the level of energy in the storage. Sometimes I say state of charge, which is not, which is a little abuse of notation, because when we say state of charge, we mean the a percentage level. Okay, so the storage is 50% charged, for example. Here, U is in kilowatt, so X is in kilowatt hour. X is the level of energy currently present in the storage. So this is a dynamical system, basically. X is the state variable, and here we are simply saying that the derivative of the energy in the storage, of the amount of energy in the storage, is equal to the power charged or discharged by the storage. So it's very simple integrator model. Then this is simply the initialization of the system, the state of charge at the beginning of our problem is a given level that we can measure, for example. Then focusing on the objective function, which are the goals that we want to keep. Okay. So first of all, this one. Here it's a minimization problem. Okay, so we want to a minimization problem, and the variable on which we act, the control variable, as we said, is U, the charging or discharging power for the storage. So we want to minimize basically this objective function. And so you see, we want to minimize here the power flowing at the point of connection of the grid, and this is consistent with the goal that I was discussing before. So here we have the p to the power of 2. So basically, when p takes a big value, either positive or negative, this function will take a big value. Okay, so we want to minimize this function. So the idea is that the solution, the optimal solution, will pick values of u such that, of course, the squared value of p is reduced. Okay, this is exactly what we want to do. So with the objective function, we put in mathematical terms the goals that the requirements that we express for our problem. Okay, so the first requirement is to keep low the power flowing at the point of connection. We need to the power of 2, of course, because we want to minimize both the positive peaks but also the negative peaks. Okay, especially in the case in which we have a microgrid also including renewable generation. Okay, in this microgrid I only included storage and charging stations, but we are working on a case in which we also have distributed generation here. Okay, and in particular wind and solar energy. Okay, so in case you have also renewable generation, then you have potentially times of the day when you have a flow of power from the microgrid to the main grid. Okay, so it's a negative flow of energy. So just to say that at the point of connection, you can have both positive peaks and negative peaks, and we need to minimize both of them. Then this part here is really related to this requirement, okay, to minimize the sock displacements from a given reference. Okay, here actually the variable x represents not just the absolute level of power within the storage, but the difference between the current level of power of energy, sorry, with respect to a reference level. Okay, so if, for example, we take as reference level of energy 50% of the storage, when the current state of charge is 50%, then this variable will be equal to 0. Okay, because this variable, I repeat, is the difference between the state of charge of the storage and a given reference value. So, for example, again, if the reference is 50 and the current value, the current state of charge of the storage is 70% full charge, then this variable x will be 20%. Okay. Here, once again, you see we take the power of 2 of x, and this means that if x is equal to 0, so the current state of charge is at the reference, then this is the minimum value that this term can take. If the state of charge is different from the reference, then here we will have a cost, a positive cost. And the idea is that we need to select u to minimize this cost here. So at the end, we want to keep the storage close to the reference in terms of state of charge, and we want to minimize the power flowing at the point of connection. Of course, there is a trade-off, as always, between these terms, okay, because Q and R, they are the weights, they are some weights, okay, and with these weights we can decide which of the terms have greater importance, okay. So of course, if we select a very large weight for this term, so if we select a very large Q, then the optimization will give more importance to the requirement of keeping the storage state of charge close to the reference value. And so we will lose on the side of minimizing the power flow, because since we need to keep the storage very close to the reference, we cannot use it for balancing purposes, and then we expect to have larger fluctuations on the grid side. Vice versa, if we select a very large R, then we focus a lot on minimizing the power flows at the point of connection, and for doing this we need to use a lot the storage. So possibly the state of charge will go far from the reference. Just to tell that, as always in optimization, I would say there is a trade-off, and so it's not trivial to select to tune, let's say, the parameters Q and R. This is an integral cost term, because you see we have the integral. We have the integral between the initial time and the final time, basically. This is a final, so-called final or terminal cost term, meaning that we once again here penalize here the deviation of the final state of charge of the storage from the reference. Okay. Of course, as you know, from calculus of variation, you can have different variants of the problem. You could even consider a problem when you don't have the terminal cost. Okay. So this is the very simple continuous time problem formulation. It's continuous time, so we have integrals basically, and we need to use the theory from calculus of variation. Now, I assume for those who are not familiar with this theory, I mean, in the reference you will find all the details and all the references to the theory of maximum principle, let's say. Basically, what we need to do, in literature for these problems, there are known procedures to compute the optimal solution. So in our case, this will allow us to compute the optimal charging and discharging profile for the storage in the service area. In this theory, we need to do what we need to do. We need, first of all, to write the so-called Hamiltonian of the system. And the Hamiltonian of the system has this formula here. Basically, we add the capital L, which is this term here, which is under the integral sign. Okay, it's part of the objective function, and then we add it to the dynamics of the system multiplied by lambda, which is the so-called core state of the system. So the dynamics of the system, you see, is very simple. It's just U. It's just x dot equals U. X dot means the derivative of x, of course. So here we have that the dynamics is x dot is equal to U. And so the Hamiltonian of the system takes this form that you see here. Then once we have the Hamiltonian, from the theory we know that using it we can write the necessary conditions that the optimal solution must satisfy. Okay, so by writing these conditions and working on them, we can find the optimal trajectory of U, of the charging and discharging power. And they are very simple in this case, just because the problem was kept very simple on purpose. So the derivative of the costate is equal to the derivative of the Hamiltonian with respect to the state with a minus sign. And if you do this operation, you get this. Okay, if you work on the Hamiltonian, you do the derivative with respect to x, you get this system. This is the so-called costate equation. Costate because x is the state of the system, which is the state of charge of the storage. Lambda in literature, PMP literature or calculus of variation literature, is called the costate of the system. So this equation, it's a dynamical equation. You see, it's a differential equation. You have lambda dot, so the derivative of lambda with respect to time, and it's called the costate equation. Then this is called in literature the equation of control, because we can find the value of u of our control variable, and it's simply that the derivative of the Hamiltonian with respect to u, the control variable, must be equal to 0. And if you again do this simple math, you get this equation. Now, this is very close to the equations that we want to get. We want to get an equation which tells us at any time what is the value, optimal value of u, which is the charging and discharging power. And this is very similar to what we want to get, because on the left-hand side, we have exactly the control variable, and this equation tells us that the control variable is equal to something. Then this term we know. We assume that we know this is W is the charging power. We assume to know how much power we are requested at any time by the drivers. Okay, it's a strong assumption, but it's relaxed later on. But at this time, we assume that we know the charging power. The problem with this equation is that here we have the cause state appearing, and we don't know yet an expression for the cause state. Okay, so we cannot use this equation like this for control purpose, because we only know W, we don't know, still we don't know the cause state. Finally, the third necessary conditions. So I repeat, these conditions, they come from literature, okay, from mathematical considerations. They are well known in literature. The third one is the so-called transversality condition, and it links the final value of the cause state, so the cause state lambda at time tf, with the final state value, so the state of the storage at the final time. And this is linked through parameter S. So S is the terminal cost. Capital S is the terminal cost. Lowercase s is just a coefficient, is a weight. Okay, it's just a number that we give to weight the importance of this term in the objective function. So these are the simple, necessary, in our case also sufficient conditions, because the problem is convex, to be used. Maybe there is a message. Okay. Okay, apologize for the voice. So hopefully now it's okay. So now we need to work on these conditions, and it's very simple in the sense that these conditions, they define what we call in mathematics a two-point boundary value problem. Okay, let's see why this is the case. So we have two dynamical equations. We have one equation, that's this one. When I say dynamical equation, I mean a differential equation, meaning an equation in which we have variables and time derivative of the variables. So this is a one dynamical equation, and it's the cause state dynamical equation because it tells us the derivative of the cause state. The second one is, of course, this one, which is the dynamical equation of the storage system, which tells us what is the derivative of the state of charge, and it's equal to the charging power. So if we take these two equations and we put them together, we have a system of differential equations of dimension 2, just two differential equations. It's called two-point boundary value problem because we are given two sets of initial conditions, two initial conditions. One is this one. So the initial value, it tells us that the value of this variable x at the initial time must be equal to the, of course, initial state of charge of the storage that we can measure. Okay, so let's say now the storage is at 55%, then x at the initial time will be equal to 55. The second boundary, this is a boundary condition because it specifies the value of some variables at the boundary, time boundary of our problem. And you see our problem is defined between Ti, the initial time, and Tf, the final time. So in this case, this boundary condition is also called an initial condition, of course, because we are specifying the value of a variable x, at the initial time Ti. Xti is equal to a given measurement, the measured value of the other boundary condition, because it's a 2-point boundary value problem, the other condition instead is on the value of the variables at the final time. Okay, and it's if we check the transversality condition, what we call the transversality condition, this one, you see that this is specifying what value the variables lambda and x should take at the end of the problem. Okay, so this is the second condition. Basically, then if we put together the two differential equations, we get this system. Okay, I just put together the two differential equations and wrote them in matrix form, and we can redefine this matrix as matrix A and this vector as vector B. And then two differential equations with two boundary conditions, and we said the first one is just the initial state of the storage. The second one is the transversality condition that we took from the necessary optimality conditions that we take from mathematical theory. So the important point is that this is just a linear time invariant system. It's well known what is the solution of this system. So when I say solution, it means that here we have an implicit model, a model that tells us what is the derivative of the variables depending on some signals, W. A solution is really the value of x and lambda at any time. Okay, it's well known from linear system theory how to compute x and lambda at any time, and the general solution is this one. And it involves then, you see, the computation of the exponential of a matrix, the exponential of matrix A. In the paper, you have the references to the mathematics, let's say, for those who are not familiar with matrix exponentials and so on. But I just want to explain the logic flow here. Okay. So the logic flow is that we are able to find really a closed form for the solution. This is very important. So we are able to compute the value of x and lambda at any time, depending on basically the initial values of the state and the costate, and the value of W. Okay, so let's reason a bit about this. Okay, we need especially to find lambda t. Why? Because we need it for the control. We see that the optimal control depends on lambda. So if we're able to find lambda, okay, then we are able to decide the optimal control at any time. We know what is the optimal control at any time. So our goal is to find lambda, basically. Here we just have lambda dot, the derivative of lambda. Here we need to find really the value of lambda at any time. So it seems that we are very much interested in this second equation, because here we have lambda. Okay. The point is that the problem is that it depends on these three things. So the initial state and costate and W. So we assume that W is known. The W is the charging power. We assume that we know the charging power at any time, the charging demand at any time. We know the initial state of the storage because we can measure it. What we miss here is the initial value of the costate. Okay, we don't know. We don't know it. So we need to find it. If we find it, then we have all the ingredients to compute lambda, basically. So in this case, it's very easy to find lambda. What we do is we use this equation and we compute this equation for t equals to tf, okay, to the final time. Okay, so we have, if we do this, if we write here xtf, basically here we need to take tf instead of t, and here we need to take tf. We need to integrate between ti and the final time tf, and also here we will take tf. Then we have the value of xtf and lambda tf as a function of the initial state, the initial costate, and W. We take these two values and we substitute them in the transversality condition, you see. Okay, so we substitute lambda tf and we substitute xtf with the value that we compute from here. So what we have at the end is an equality in which we have appearing lambda Ti. I don't show the passages; they are in the paper. But basically, it's like I said: if you plug XTF here and lambda TF here, you will have an equality which depends on in which the variable that we want to find is lambda TF, and so. Basically, you can find, using the transversality condition, you can find the initial value of the costate, which is exactly the parameter that we were missing. This nomenclature, I will introduce it later on, but basically these are coefficients, they are just numbers, okay? This is the initial state that we know, and then we have an integral between Ti and Tf of, these are other numbers, multiplying the W, the charging power demand. So what is important to understand is that at the beginning we can compute the value of lambda Ti, okay, and it's the value that once we have it, we can compute lambda, okay. Once we have lambda Ti, we can compute lambda at any time, and once we have lambda at any time, we can compute the control at any time. Okay, so imagine I am at the beginning of the day. I know what will be the charging request for the entire day, W for the entire day, the profile of W for the entire day. I'm sorry I don't have a picture here for the moment, but imagine that you know what is the power level of W, the recharged power that is requested for the entire day. It means that at the beginning of the day, by doing this calculation, simple calculation, I'm able to compute the initial value of the costate that then I can use to compute in real time the control action for the storage that yields the optimal solution to this problem. The key is that I am assuming here I have an integral between Ti and Tf, and I have W appearing here. So we can do this only if we know really the charging power that will be requested during the day, of course. And this is a strong assumption. In practice, we only know an estimate of the amount of power that the end users will request during the day. This is the weakness of the approach that needs to be addressed. Okay. So the initial costate depends on the realization of W. The realization of W means depends on what is the effective, what is the actual, profile for the recharging power. But basically the procedure is very simple, and it's simple exactly because we kept simple the model here. It's too simple, I should say. It's simple integrator. Now we are working, as I would say, on this same problem where we have a much more realistic modeling of the system, and of course the mathematics is much more complex. So these symbols, they are basically the elements of the exponential of the matrix A, which can be computed exactly with any symbolic computation tool. Okay, so all these symbols that we saw before, they are basically hyperbolic trigonometric functions. The important point is that from theory we know that this matrix, that it's called Hamiltonian matrix, is unstable, and this creates some difficulties if we need to perform numerical integrations. Okay, this is another weakness that we need to be aware of, basically. So this system, this two-point boundary value problem, is unstable. Okay, there is an eigenvalue that is positive here. Now, we also addressed the same problem by reasoning on another setup of the charging area. So in the first setup, you see the electric storage system and the charging sessions, they were, we say, in parallel, meaning directly connected to the point of connection with the grid. It's very interesting to also examine the case in which instead the storage is in between the grid and the charging stations. Intuitively, why is this important? Because in this problem, the element that adds uncertainty is the charging demand, because in practice we don't know when a user will come to the charging station. if he will plug or she will plug the electric vehicle exactly at the time we expected. We don't know how much energy the user will need to recharge. We don't know the exact level of the charging power, and so on. So actually W, it's a stochastic signal. Okay, we don't know it exactly until it really happens. So if we place intuitively the storage in between the elements that adds uncertainty and the grid that we need to preserve somehow, then the storage will absorb the fluctuations. We will use, as we see, the storage to absorb the fluctuations coming from the charging demand. Now, this is an intuitive sketch. Of course, in literature, they are studying in these years schemes to realize this kind of concept. Okay, so basically, the setup looks similar, but we have one converter more here, and basically all this part is in DC, while the AC part is only this one. Okay, so as soon as we have contact with the grid, we have a connection, we have a conversion stage. This is a sketch, simplified sketch to see how this concept of using the storage in between can be realized in from the electrical point of view, let's say. Now, we gave an equivalent mathematical formulation for this second setup. Now, I will not spend too much time here. It's very similar. Just notice that here before we had P, because P was the point of the power at the point of connection with the grid. Now this role is taken by variable U. Okay, so in this case, the storage has two inputs. One is the power from the storage is directly feeding the charging stations from one side, only the storage, and on the other side, the storage is connected with the grid. So the storage here has two inputs, while of course before the storage you see had only one input, one point of contact with the grid. So it's really radically different. And now we need time to check it in details, but you can realize this scheme with this connection here. Okay, so still we have one input to the storage, but thanks to the presence of this converter in particular, you are able to do what is supposed to happen here. Okay, so basically here instead of P we have U, because this time U is really the power flowing at the grid, and also the differential equation modeling the storage is different, because as we said we have now two inputs for the storage. So so the level of energy in the storage will increase because of U, if U is positive. Okay, so we have energy entering from the grid and energy leaving and going to the charging stations. Okay, so we have plus U minus W. X dot is equal to U minus W. Now, I'm not showing it here, but if you repeat the calculations from the theory of calculus of variation, so if you compute the Hamiltonian and you write the necessary and sufficient optimality conditions, you realize that the two setups have the same solution, which is surprising, but not that much if you think about it. But this is very useful from the practical point of view, as we will see. Now, I'm stressing here always the fact that we are in a deterministic case. With this, I mean that we assumed, as I told, to know exactly W, the value of W. So the amount of power that the users will request during the day. And this is a strong assumption. We use it only to be able to set up these mathematical problems and find a simple solution. In reality, we need to work on a stochastic case in which we cannot assume that we know W exactly. We cannot assume that now I know exactly what is the power that the users will ask to recharge at 5 hours from now. It's unrealistic. because we have a lot of uncertainty on the arrival time, the number of users that will arrive, how much energy and power they will request, of course. So it's instead realistic to assume that we know the expected value of this power, charging power. Okay, so just to tell you that actually the focus of the paper that I presented before is on stochastic optimization, in which we want to optimize the expected performance of the system. Okay, this is what we can do in reality, since W is uncertain. What we did in that paper is to find a solution to this problem, which is the stochastic counterpart of the problem that I just presented, by using the solution, the simple solution that I presented so far of the deterministic problems. Okay. At the end, we have a control law that is in continuous time, so it's very simple to compute. And you see, it's very simple to compute because at the end you need just to, this is the equation. It's just multiplications and subtractions. The difficult part is in these integrals, in computing these integrals, okay, but you can do offline at the beginning. Then we were able, let's say, to find a simple solution to this stochastic control problem. It means that if we implement it, we optimize the average performance of the system. And the details are in the publication. Let's see some pictures to give an idea of, in practice, the things that we discussed. So, so imagine we are controlling the charging area over 12 hours. Okay. So in gray, this smooth profile is the expected value of the charging power that the drivers will ask to recharge in the service area. And as typical, we have two peaks. Okay. In black, it's what we call a realization. So, as I said, it's reasonable to assume that we know an estimate of the charging power requested. But then, if we go at the end of the day and we check the power that we were asked, that the users asked to recharge, then we will likely see these very fluctuating profiles, okay, where you see charging sessions that are ending, so you have an abrupt decrease of power, charging sessions that are starting, so you have an abrupt increase of power, and so on. Okay, so this is the expected value of W in gray, E of W, and actually the real W in black. This is the plot of the control of the storage. So the control variable here is the storage. So we have shown here the control of the storage in the two setups. Okay, the setup 1 and the setup 2, the two setups that I've shown. The control of the storage in setup 1 is this in gray, is this one in gray. Okay, so this is the power that the algorithm tells us to charge and discharge from the storage. So if we adopt setup 1, we have very smooth profile from the storage and a very, you see, smooth profile for the state of charge. In setup 2, instead, the control of the storage is much more variable and fluctuating. And also similarly, the state of charge as well is noisy. You see, it's noisy. Okay, this exactly because in the setup 2, the storage, you can think that the storage has two inputs. And one of the inputs is W, which is, you see, a profile that is very, very uncertain and variable. Okay, so this will be reflected also in the control of the storage. But the good thing about setup 2 is that it allows to achieve very good performances in terms of power flowing at the point of connection with the grid. So here instead, the black profile, this is the power flowing at the point of connection with the grid, which is really the variable of interest for us. We want to keep it low, as low as possible. So you see that the black profile, which is the optimal control, or optimal result from setup 2, is very smooth and low. While the negative point of setup 1 is that you see all the uncertainty on the charging power goes into the grid directly. Okay, there is no way to prevent this, just because of the infrastructure setup. So you see that the optimal profile for setup 1, the one in gray, is very, very fluctuating, and it has very large peaks. But overall, observe that here we have a peak of almost 300 kilowatt. Okay, and in any case, it's very much reduced using the technique. Okay, so the peak of 300 kilowatts of charging, it's reduced to less than 100 kilowatt for the setup 2, and even in setup 1, we have less than 150 kilowatts. So it means that at the point of connection of the grid, we will be able to reduce the impact of the charging sessions. Setup 2 is the best for this kind of scenario that we have seen from simulations. Then some considerations. We considered a very simple model for the storage, as we saw. Now we are working to consider constraints, because here, if you check, we don't include the important box constraints. For example, on the power of the storage, which is limited between a minimum and maximum value, the state of charge of the storage is between 0 and 100%. The power flowing at the point of connection of the grid, which has a minimum and maximum value. If we include these constraints, even if they are trivial constraints, the mathematical theory that we need to use is much more complex. Okay, so everything becomes much more complex, and we are currently working on that. Also, we are working on more refined models for the storage, and in particular, we are including losses and degradation. So already with these schemes, you see that we need to include the conversion losses for the converters, and also we need to model the loss of life and calendar aging of the storage. This is very important, and also modeling degradation is very important to make sure that we are not ruining the storage with the control. Okay, so we are controlling it to solve a problem, which is to lower the point of the power at the point of connection of the grid, and maybe at the same time we are degrading too much the storage because of the control action that we are applying. We want to avoid this. Okay, so in the current works we are embedding also detailed degradation models to avoid that we have this problem. The strong point of this technique is that it's online control. Once you compute the control, it's very simple to apply. You don't need any particularly strong computation capabilities or machines. Even small hardware can do it really easily. The point is that we need to have a prediction of the charging power. Okay, but we are working also on this with stochastic control. Okay. So once you improve the mathematical formulation, then the two-point boundary value problem becomes much more difficult to be numerically integrated, and this is what we are focusing on this. We're also focusing a lot on stochastic, on improving the stochastic modeling of W to shift really to full stochastic optimal control. Just now, a few slides on a very close problem, which is a problem in which we want to control smart charging, slow rate smart charging, meaning the scenario I was mentioning where we have that the car is connected for a very long time period. And in this case, we used model predictive control. So in model predictive control, basically, the process is like this. We have a process we want to control, which is the cars, the electric cars in this case, then what we do is at any given time, we acquire a feedback from the car. So in particular, we're interested in the current state of charge of the car, of the battery. Then we solve an optimization problem, and the result of the optimization problem is the control sent to the car. In our case, the control is the charging power that the car should, the amount of power that the car should charge or discharge. And this is in discrete time and iterative. Okay, so if we want to visualize it, it's a three-step approach. So at any given time, we acquire the feedback from the process. So we measure what is the current state of charge for the car. Then we build and solve an optimization problem that goes from the current time to a time in the future. So for example, we want to control the charging over the next 1 hour. We solve it, the first control variable will be applied. Okay, so for example, we solve the problem, and in the next, we know how much the car should charge or discharge in the next 5 minutes. And then after the 5 minutes are elapsed, we repeat the process. Okay, so we go one step ahead, time has moved. Okay, we repeat the entire process, and we know what is the charging level for the next 5 minutes. 5 minutes just because it's the time step that we used in the first algorithm, and so on. So you see, it's a discrete time. It goes 5 minutes by 5 minutes, if the sampling time is 5 minutes, okay? And we need to build and solve an optimization problem. We apply the first computed control variable, the other ones we just discarded. And you see, it's really iterative. You compute, get feedback, compute the control, apply the control. Then after the time period has elapsed, you repeat the same. You get the feedback, you compute, you apply the control, and so on. So this is a centralized formulation, and the goal was to control a fleet of electric vehicles at the level, for example, of a neighborhood, or even at the level of entire city. We did this in Rome in cooperation with Enelix, and actually we tested, as we will see, these algorithms on the real systems. So the difference with respect to the previous approach is that this is discrete time, basically. So at any time, you acquire a feedback, and you need to build and solve an optimization problem, which is complex. So you have a lot of work online in this case, in the sense that at any sampling time, you build and solve an optimization problem, which can be very, very complex. In the previous case, instead, most of the work you do it offline. You do a lot of work, theoretical work, to compute the optimal solution. Once you find the optimal solution, it's very simple to implement, and then you don't need to do other optimization steps. You just have the formula of the optimal solution that you need to implement. So this is the radical difference here. You need to have good hardware, I would say, and especially good mathematical optimization solvers that you use continuously. Every 5 times you need to repeat this process. So it's really different. The advantage of then you would say, why this solution? The advantage is that with model predictive control, it's much easier to include detailed models and detailed constraints. While, as I said, if we want to include detailed constraints in the previous approach, the mathematical theory we need to use becomes really, really very, very complex. So this is a reference publication of mine. If you want to check in details, let's say this other problem in which we use the model predictive control, and this has been really tested, and I think it was one of the first real tests in the world of this kind, together with Enel, on real vehicles, on the real infrastructure. And there was a lot of problems also related with standards that were evolving, related with the technology of the cars, which of course is not open source, of course. The original equipment manufacturers, all the parameters of efficiency, battery degradation, and so on, we needed to estimate them from tests. And so here I'm just presenting some slides to describe this. This is an interesting point. So the overall goal was to control the aggregated charging power. So every color here represents a different car. So we have many cars that are recharging simultaneously. Here we want to, from the perspective of the user, we want to save money. So we want to optimize the charging process, for example, using renewable energy when it is abundant and so on. From the perspective of the grid operator, we want to control the aggregated charging power. So this curve, total curve, is the aggregated charging power. And we want to shape it in a way that it's useful for the grid. Okay. So, for example, in weakly connected grids, we can easily consider periods of the day, for example, when you don't have power. Okay. And so you need to manage your resources to make sure that you can face also these obstacles and so on. Or a typical idea is to maximize power from renewable energy. In this case, we did something even more. We used and we controlled in real time these cars to provide ancillary services. An example of ancillary services, it means that at a given time, the operator asks to change the shape of the aggregated power. Okay, so here you see we have a big reduction of the power, because maybe at that time there is a problem in the grid and we are asked to provide this service, and the service is to reduce the power consumption, and this can be done dynamically. Okay. I thank also Professor Alessandro Di Giorgio, which is the colleague with whom I've worked all these years on these problems. Nowadays, we are the drawback of this is that you need really a lot of computational power to solve this problem, especially if you have many cars. If you have hundreds of cars to manage, it becomes a huge problem, and it's very tough to solve from a computational point of view. We are now exploring decentralization methods, and I've seen that there are talks discussing decentralized energy control in combination with 5G that provides really low latency communication to be able to transform this problem that is a centralized one in a fully decentralized one, which is very simple to solve. Okay, this is what we are doing right now in the project 5G solutions. Really, few slides on the Foveos 2, which is on model predictive control for smart home control. This is the reference paper, quite old, but it's a reference good paper on this subject. The scenario is a microgrid or a building in which we have legacy appliances, so appliances that you cannot program, smart household appliances, storage units, you have renewable power, you have possibly other storage elements like electric vehicles, and so on. The idea is to control all this complexity with a controller, which will host the algorithms that I'm going to present. And the idea is to satisfy these requirements. So this is a smart home controller. So typical requirements that we can really easily address with this control technique are maximize self-consumption of power from local generation. So in many cases, we don't want the local green energy to go in the grid lost. Okay, we want to use it really locally for the local community. From the perspective of the user, we want to minimize the cost of energy consumption, especially when we have time varying tariffs. So we can have very expensive periods of the day and very cheap period of the days. Then the user needs to do works, needs to execute some household appliances. It can be residential users, it can be industries that need power really at some periods of the day, and we cannot let them down. So we need to satisfy really 100% these user preferences, we say. Okay, and then of course the aspect of efficient use of the technologies. If we have a control that achieves these goals, but after 1 year it has ruined totally the storage, then it's pointless because it's very expensive element, the storage. And then we want to have a controller that can interact with the upper level actors of the grid to provide ancillary services, okay, so that it will be really an active node of the energy system. It will be able to provide services to the grid. And the idea is that we used event-driven model predictive control. Very simply, the idea is that if we have the time flowing, at any time we can have an event that is acquired by the algorithm, and the algorithm replans all the activities to fulfill what has been asked. So it can be a user that requires to start a new household appliance. It can be an industry that is requiring to start a process. It can be some electric vehicles that are recharging. It can be the grid actor that is sending the demand-side management signals, so for example, to reduce the power consumption, and so on. So in that paper, you will find the formulation, the full formulation. Basically, the key ingredients are, as I said, minimize costs, maximize self-consumption of energy, respect 100% the user preferences, avoid overloads, especially in dynamical case, for example, weakly connected grids, when you can have that in some periods of the day, you have really low power coming from the grid, and you have to take this into account. This is just an example of the final, let's go here, how the final planning of the day goes. So this algorithm and this smart home controller is able then to plan and control in an efficient way all the different elements like storage, electric vehicles, micro generation, the presence of thresholds that are dynamic in the day. In some periods of the day, maybe you don't have any power from the grid, and the controller needs to be able to take this into account, and so on. This is a view of all these colors are different loads or the electric vehicle energy or the storage energy, and so on. So full details are in the paper. And then I would stop here, and I would thank you very much for the attention. To summing up, I just conclude saying that I presented two different approaches, one continuous time based on PMP, one discrete time based on MPC, which are very, very popular nowadays. And we are doing a lot of effort also to merge these two approaches, also using something I did not discuss, which is reinforcement learning, so some machine learning techniques. The fusion of these techniques is really, I believe, something very powerful that can be really useful in real problems, okay? What I said is that we always focus in network control laboratory really on applying mathematics to solve real problems coming from real user requirements. So I close here. I went a bit fast. I hope it was interesting. Full details in the paper, and of course, feel free to contact me for any additional explanation. I will. Sorry, I did not put. I just realized I did not put my email. I will try to. I will write it here. If the computer assists me, so it's liberati@viac. This is my mail. Feel free to drop me an email in case you have additional questions or questions. Okay. Thank you very much.
Thank you so much, sir. Participants are requested for the queries. Participants are requested to raise the queries.
Should I remain on this link for the questions, or should I change? Should I go to another session for the questions? No. Okay, so I'm available for questions in case you have.
You can just stop the sharing of the screen.
Okay.
Yes, participants are requested. If at all you have any queries, you can raise it now. Okay, sir, we have your mail ID. Dr. Francisco Liberty, we have your mail ID. Surely the queries will be raised out after the session or before the completing of this faculty development program, we'll be connecting you the queries via mail ID. And I'm very thankful, sir, that you have been sparing your valuable time in your busy schedule. So, the participants, the keynote speaker for the session 5, Dr. Francisco Liberati. He has been explained about the electric vehicles for the fast charging method, also given knowledge about smart charging of electrical vehicle through smart grid in a controlled manner. He also focused on the optimum control of charging method such as deterministic method so as to make the charging more faster. So this is the overall summary in short regarding the session what we had from Dr. Francisco Liberati. Thank you, sir, once again from my side on behalf of BIT Raipur. Yes, sir. Vaibhav, sir, any queries? Okay, thank you, sir. We have been connected, and we will meet you soon in the future FDPs for sure, and we'll connect you personally, sir. Thank you.
Thank you very much again. It was a pleasure and an honor. Okay, thank you very much for the kind words. Okay.
Thank you, sir. Thank you.
I need to leave for a lunch, so we keep in touch in the future. Any queries, don't hesitate to write me. Really.
Surely, sir. Surely. Yeah.
Goodbye. Thank you.
Bye-bye, sir. Participants are informed that the day 2 sessions 3, 4, 5 has been entered and successfully. Day 3 session will be initiating on tomorrow at 10 a.m. So you are requested to connect by 9:50 a.m. on tomorrow. Thank you, one and all. Participants are requested to attend the practice test. The link has been shared already. Daily one practice test is being required. And session-wise feedback links are also being shared time to time.